Ready to go? Okay. Okay, so good morning, everyone. And for this final lecture, I want to cover this dynamics of interfaces and the KPC universality class. So first of all, at the beginning, I promise you that I'm not going to change the models. In fact, I will not. I keep to that promise, but this is sort of one very particular class of interesting initial conditions, right? I just want to emphasize that I'm not going to look at something totally different. Okay, and the second thing which I want to say is that this is a paper from 1987, which was quite influential. I mean, then it was partially forgotten, and then around 2000 somehow, because of various things to which I will come, things became extremely popular, and that was sort of a very, very strong push to the field, and both from the experimental side and also from the probabilistic and mathematical side. And so now suddenly, KPC, many people know, and it appears in other physical systems. And so, I just thought that, to have one topic which is sort of still very active, and then, lots of things are happening, might be useful to sort of cover this in some introductory way in these lectures. And so the first thing what I wanted to explain you is, what kind of interfaces we are looking at. And so this is sort of 7.1, this motion of interfaces. Of course, the title is very general, but what I want to do is, I want to explain what kind of interfaces we look at, and what I mean by this motion. Okay. And so I'm coming back to, model which we had already quite some time ago. So this was Glauber dynamics. So it's a reversible dynamics. So this is spin flip. And I'm doing icing. And the dimension is equal to 2, right? So this is what I explained already, so I will not repeat. But now I want to do a special initial condition, and that's sort of, you have the phase diagram. So if I'm at low temperatures, you will have the plus state, where things are mostly up, and then sort of just by reflection, you also have the minus state. And so it's clear that what I mean by an interface is that I simply join these two faces along a line, and I will do this in a very particular way. Namely, if this is sort of my underlying lattice, I will put the interface like sort of in these steps here. Okay, like this maybe. Okay, so you should think of the underlying lattice which is sitting over here, and now I want to make an interface between the plus phase and the minus phase. So out here, you imagine that just everything is minus, here everything is plus. Okay, so that's a rather easy construction. And so now we have to think about a little bit, which parameters we tune for the dynamics. And so you remember that I have the spin flips, and of course, I can think of having like an external magnetic field which sort of makes the spin flip slightly unbiased. Maybe they want to have more plus or more minus. I will come to that, right? So this is what I will discuss. But the first case which I want to do is I want to do the stable to stable case, in the sense that both pure phases are perfectly happy, and if you want to have a diagram, then you have these two states minus and the other one plus, and then you think of some potential function which sort of looks like this. But the point is, it's perfectly symmetric, right? And so you jump between the two with equal probability. And of course, maybe I don't want to freeze everything completely. So maybe I still have a small temperature. Then what will be happening is that with a very small probability, way out over here, maybe a plus is created. So you have a nucleation of the other phase, which in this case sort of will very, very rapidly decay. But I just want to point out that there could be something out there very far away. But I'm just concentrating on the on the interface. And for the motion of the interface, I mean, this sort of small errors, which then may become actually relevant, don't play any role. Okay, so that's what I'm doing. And now what is well, okay. So the first thing is okay. So the stable to stable means that you see what I can do is you know, I'm in low temperatures. I don't want to break any bonds, and so I mean, for instance, what I could do is this spin, which is minus, I mean, could you know, move to a plus, and then it looks like this, right? I mean, so this has disappeared and looks like this. Or of course, you know, I could have the opposite. I mean, that this one is now moving to a minus, and so this has disappeared. And then, of course, it can flip back again. And so you see, we'll see that this interface is clearly moving, right? It's not frozen, but it can move, but the moves are somewhat restricted. And now, why is this related to the kind of models which we studied already? Well, I mean, that's sort of, you know, a very trivial observation. I mean, you go to this coordinate system, which is 45 degrees, and then you know, in this coordinate system, you will have now an interface which is sort of going up in units, and then it's going down maybe, etc. Right? I mean, so I'm not doing a terribly good drawing here at the blackboard, but I mean, this is what you would think. So it's piecewise linear in units of the lattice, and has slope plus or minus 1. It's just this rotation. And now what we are saying is that we have two moves. I mean, you know, if I have somewhere a local maximum, then it can move to a local minimum. You see, I mean, I fill this up. I mean, then, you know, this minimum will move to a maximum, or maybe I remove. I mean, then this maximum will go to a minimum, local minimum. And of course, I can do the reverse. And since I assume that these things are equal, I mean, then, you know, both of them have rate 1. And so you discover that, you know, in this model, I mean, it so happens, or, you know, by construction, if you want, so, you know, there's sort of, in principle, you know, if I take a system and then I look at the interface between two faces, you know, the bulk and the interfaces are, of course, coupled in a complicated way, and then you have to think about what would be an effective dynamics of the interface and all these kind of things. But in this case, you know, for this very special model, you have directly, without any further effort, an effective dynamics for the interface. You see, I have now completely forgotten what happens out here. All right, and so you see that this is nothing else but the SEP. And of course, you know, I mean, the particle is sitting at the downhill, and so this particle can jump over here. And so here the particle is sitting at the downhill, and that's jumping over here. And so you see that I have simply the symmetric simple exclusion, and that's it. Okay. Now maybe you want to ask a question, and I mean, one of the, I mean, what would be a natural physical question? I mean, you see that this is an interface with any fluctuations, and so you might wonder, as the dynamic progresses, how does the interface roughen, right? I mean, so it just develops fluctuations, and, you know, I mean, presumably, you know, there doesn't seem to be any mechanism. You know, I mean, there's no frictional mechanism which would suppress fluctuations, and so so the question is, how do the I mean, it's roughening, but you know, how fast is it roughening? I mean, that's sort of the question, right? And so, of course, now you could do a computation which I showed you at the very first lecture, namely you could look at the methods of moments, and you can figure it out for this model, but you know, first of all, I don't have so much time, and secondly, you know, we know already how to do a little shortcut, and so let me just do the shortcut. So now I do again what we discussed yesterday. I do the Landau-Lifshitz, and for this, you know, I'm going back to the SEP, and if I want to include fluctuations, I know already what to do. I mean, so, you know, if I put the fluctuations away from let's say this uniform profile, then what we found yesterday is that you know, there will be a second derivative sitting over. Well, maybe I write it. We had it. I mean, so there will be a dx, and there's a second derivative in phi, and then there will be this white noise, right? I mean, this was, now there were coefficients, but somehow, you know, we have here, you know, if I take this particular slope, I mean, then, you know, you know, you can sort of imagine that you know, we have here sort of a uniform system here with density 1/2 in the way how I've plotted these things, and so, you know, its coefficients are just taking at 1/2. Maybe I didn't say this. Of course, you know, I put here, you know, this simple slope which corresponds to 0, 1, 0, 1, 0, 1. I mean, of course, I can put here other slopes, right? I mean, but I just don't want to. It's for what I'm discussing. You know, this one slope suffices. Okay, so this is the equation which you know, and then you know, when you go from here to here, then it's clear that you know, so I have to introduce a height field. So here, this is the height, and here is my lattice height J, and so you see that if I take the derivative of the height, or maybe minus, okay, this is plus, maybe minus the derivative anyway. So if I take the derivative of the height, then I get to the particle description. And so you see that here's this derivative. And so if I write down the equation of motion for the height, then this will be the second derivative of h. And now this has been going out, and so I just add the white noise over here. So it's a diffusion equation, but now I add white noise, right? Yes, question?
Height may not be a well-defined function.
Excuse me?
Height may not be well-defined here, right? Because
height will not be well-defined, why?
the function may not be well-defined. Because the function can go like this.
No, well, it doesn't. In my case, it doesn't.
As a function
Because,
of j,
I
can't
mean,
it?
you know, it's a piecewise linear function which has slope plus and minus 1, so.
But it's 2D-izing, right?
No, it just keeps going. I mean, you know, of course, physically you might have, you know, more complicated overhangs, but there are no overhangs here.
Mm-hmm. So do you like consider a particular part of the interface which is?
No, for any. Well, I mean, of course, if I, you know, I just sort of okay. If I assume this type of initial condition, you will never develop any overhangs.
No,
That is what he's asking, that these stairs that you have drawn, that is why the question is coming from, that height, it seems, but it is tilted.
no, I'm saying the interface could be a bubble, like a Paris
Yeah,
droplet.
sure, could be a bubble. But I mean, if I start with this initial condition, the bubble will never appear.
Uh-huh.
That's, you know, because I mean, you know, look at my dynamics. I mean, you know, this is the height. How do you want to, I mean, I understand that, you know, in general, you might have a bubble over here and plus and minus out here. That's correct, of course. But by fiat of my initial condition, I excluded this to be happen. Because, you know,
so the initial
this is a one-to-one mapping. How could you ever have a bubble?
Uh-huh.
You see, one thing you should have, which I completely agree, that, you know, I mean, this is what I was trying to explain. I mean, you know, if I really look at the dynamics, that with a very small probability, you might produce somewhere this bubble, right? But I said that this is on a time scale which I'm not interested in.
Okay.
And in this model, clearly there will be no overhangs, right?
Mm-hmm. Okay.
All right. Okay, so now we have to do this exercise, and so at the initial time, you know, I started with a flat profile, so this is equal to 0, right? And so I can write down the solution of this equation. So let me just look at the height at 0. Well, that's the integral from 0 up to t ds. And now there comes, you know, the motion according to the heat equation with the Laplacian, and of course there I have no the fundamental solution. So I have the transition probability for this one, which is just sort of the Gaussian, and so here I have okay. So here I put this transition probability from t minus s, and now I'm at 0. I go to an intermediate point x, then I have to do the integral over dx, and then I have the psi of x at time s. Okay, so this is the solution to my equation. So this is just the Gaussian kernel, which gives the fundamental solution of the diffusion equation. Okay, and then I'm just integrating the noise, and okay, so that's the correct thing. And now you know, it's a nice exercise to compute what is okay. So maybe the first observation is that, of course, the height average is equal to 0, because when I average here, the noise is 0 and zero. But I want to know what is the roughening, so I better look at this quantity maybe. And now you see that I get the square of this one, but there's a delta x prime, and so I can do this integral, and then I simply double the time. And okay, and that's it already. And so what you get then is c, and then you get then but then if you do the square, then I mean this intermediate variable is integrated out, but I get 0 to 0. I mean so what I find then it's pt p of 2t, and then it will be 0 0, right? And that's dt. Okay, so this is the answer. But now you know what this, I mean, 0 0 means that, sorry, I mean, there's an s. I have to integrate over intermediate times. Okay, and that of course, this is the integral from 0 to t of 1 over square root of s. And so this will be square root of t. Okay? And so you see that the interface actually roughens. Is of order t to the 1/4. Okay, so you might have thought that it goes like a random walk, but it doesn't. I mean, because it's an interface, and so actually the fluctuations are only of order t to the 1/4. All right, so this was fine, but now we want.
Just a confusion. Phi is the local magnetization, is it? On your left. Sorry. Right.
Here.
Sorry. Is phi local magnetization initially, and then from phi
is phi. Well, it's what I explained yesterday. It's the Landau-Lifshitz theory, which is sort of the deviation from. It's a continuum version of this curve.
I was wondering, from phi did you derive h, or you wrote h just as a?
I'm just trying to say that in a somewhat naive continuum approximation, this is my central equation, right? And that's a somewhat naive continuum approximation to this discrete evolution. That's all.
Okay, not directly from phi.
No, nothing more deep. Okay.
H prime is equal to roughly H prime is phi. H like derivative of.
Yeah, so these are erased. I mean, so the h prime is equal to phi. But just sit it here, yeah.
Can you explain why phi h prime is phi? I don't understand that.
What?
H prime is phi.
Okay, so if you look at this picture, if you take the derivative, you will find the particle configuration. Are you agree on that?
Okay.
Yes?
Yeah.
Yes or no?
Yeah, thanks.
Okay, I mean, when slope -1, you have a particle, and if there's slope +1, you have no particle. So this is how you get this equation, right? And then if we agree that this was sort of, what we agreed yesterday, that this was, slightly rough, but a good way to describe the fluctuations in the SEP, then you automatically arrive at this equation, right? All right. Okay, so now let's see what I want to say. Now comes sort of the more interesting case, namely what happens when you do stable versus unstable, metastable. No, it's not unstable, it's metastable, right? Okay, and so now my picture has changed a little bit. I mean, so I'm saying I want to have, let's say, I want to have the plus advancing into the minus, and therefore, the potential which I draw is sort of a little bit higher for, let's say, this is minus, and then, it's sort of deeper over here. This would be the plus. Okay, and now you see that this mapping, of course, is still true. But now these ways have changed, and so if I call this again Q, and if I call this P, then you see that from the SEP I'm going to the RSEP, and most of the time I will actually go to the TARSEP. I mean, so this means that Q is equal to 0 and P is equal to 1, right? I mean, so this interface is sort of, now it's metastable, and now, of course, because it's metastable, it means that, in fact, I will have this nucleation far apart, but that's okay. I mean, I'm still ignoring them, and what happens is that, once in a while, I sort of add here, and you know, this opposite process is sort of forbidden. So basically, if you think about this initial condition, I only fill up local minima, and local maxima I don't care. All right, so this is fine. And now, of course, the big question is what happens to the Waffening? Right?
Sir?
Let's see. Let's see.
Excuse me, sir.
Hmm?
In the box, to your left. In the box equation, shouldn't there be a space derivative before the noise term?
In which equation are you looking?
Yes, that equation.
Yes.
Before the noise term, shouldn't there be a space derivative?
No, because you see, I mean, here there was one derivative, and this goes out because, you know, if you take the derivative of this equation, I get one derivative here, I get three derivatives here.
Yes, sir. And the noise term, shouldn't there be a derivative?
Yeah, that's what I've had been up here. Yeah.
Right. But in
I
the
just look at the. Okay, so I differentiate this equation. So I get h prime, I get h prime, and I get this prime. No. Just differentiate this equation with respect to x. Then I have
Yes.
three terms, and each one of them I have to differentiate.
right.
Okay, and then the h prime is equal to phi, the h prime is equal to phi, and this is psi prime, which I've written up here also.
Right.
Because I've written this outside the bracket. It must be a conservation law.
Okay. So that okay, then psi dash should be the space derivative of the noise term.
No,
right?
it was correct the way I've written it. I mean, sort of, there's nothing to be modified.
Um,
No, still not happy.
The derivative of the second equation gives you the first equation, so they are completely identical.
all right. Okay.
All right. Okay. Okay. So now let's see. What did I want to say? Yeah. Okay. So now let's before we enter into the issue how what is the Waffening? We just want to think about maybe some other initial condition which we could think of, which actually sort of have been realized in the experiment. I mean, therefore, I don't want to list arbitrary initial conditions, but initial conditions which are, so to speak, of interest. And so what we had so far. So I have to put this. So far we had what people call flat initial conditions. I mean, this means that there's no noise in the initial condition, no noise. And another option, of course, would be to say, okay, I mean. Maybe we have already some sort of initial noise in this thing, and then one natural initial noise would be, rather than taking, 0, 1, 0, 1, 0, 1. I mean, just like what we do in the TARCEP or in the RCEP, that we say, initially, sites are occupied with some probability and empty with some other probability, and then. In terms of this interface, this would mean that we have a random walk interface. Random walk. Let's see. What did I write here? Yeah. Okay. So let's say a random initial, but what we mean is really a random walk. Okay. But then there's another initial condition which initially you might be not. Sort of immediately anticipate, but in fact it's a very important initial condition, namely, you will see in a second why it's important, but we can imagine that we put the minus like this and we put the plus out here. Okay, and now it's easy to see, and then we are still in the completely asymmetric case, then it's very clear to see what's happening. You see, I mean, at the beginning, the only move which I can do when I do not break any bonds is that I can fill, this little square over here. Okay, so but once I have filled this, now I suddenly have two possibilities here. I can fill this one or this one. So maybe I fill this one. And remember that according to our rule, what we do is that, whenever we can flip, whenever we can fill, we do this after waiting time, right? I mean, so this filling process sort of, picks up some random site, and then it waits for this exponential time, and then it just keeps going. Okay, and then if I turn this now again to my 45 degree, then you see what I have is something which looks like this. I mean, so on a large scale, I have this interface which sort of touches the sort of the boundary, and of course superimposed I have some fluctuations. Okay, so this is now my height as a function of j. And now, it's not too difficult to imagine that physically, I sort of complete this to a full droplet. I mean, that's what you wanted to have, right? And I'm just looking at one segment of this droplet, right? I mean, so this is what people call, either droplet or it's also called step initial condition because, when you think in terms of the TASEP, I'm just sort of, filling sites up and then everything is empty, right? I mean, so either one, okay? All right, so that's this part, and now the next part is that I want to come to this experiments by Takeuchi. So the first time I heard about the experiment was in 2009 when he was visiting Munich, and he showed us, the first experiment, which was sort of an extremely surprising and an exciting moment. And then of course he spent a lot of time in analyzing this more carefully. And of course, he knew about all these things better than anybody else. And for his PhD thesis, he was somehow, so he's sort of in a lab of surface sciences, right? And so he was just absolutely fascinated and wanted to see a real experimental realization of this, okay? And so he spent a lot of time to figure out what kind of system he should take, and then eventually sort of he came up with this very beautiful idea that, so this is now the Takeuchi. And so, he talked a lot to engineers. So he had from the beginning sort of the idea that maybe one should use liquid crystals, but they have a complicated phase diagram. And so he talked a lot to engineers to figure out in which substance and which parameter space one should do. But this I cannot tell you. I'm not an expert on these things, but I just want to explain you a little bit, what the experiment is, what he did. So basically it's something which you can sort of just hold in your hands. This kind of cell, I don't know, this is maybe a centimeter or so. Anyway, so you have two glass plates which have about a small distance, and but then it has sort of, it's like the square has some extension, and in between, you have this liquid crystal. And so, here you have sort of some of these crystal things. Actually, what's happened sort of microscopically is sort of a little bit unclear. You see, when you look at the details, it's actually quite complicated. But for the purpose of the experiment, the main point is that he can tune parameters, and it's somewhat more tricky than what I'm explaining, but for us it's enough. He can tune parameters in such a way that this thing is here metastable. Okay, and so the question is, how is he going to see the difference between metastable and stable? And that's fortunately very easy. So you do a light transmission, and then you sit in front of your computer, and then you basically see the transmitted light which goes so the light is sort of going through here, right? And then you observe it, and magnify it somewhat, and then you observe it. And the point is that if it's the metastable phase would be essentially gray, so it's just sort of some fluctuations, but essentially gray, and the stable phase simply simply doesn't emit any light. I mean, so this will be completely black. Okay, and so he carefully has prepared, the metastable phase, and then you sit and you watch, and nothing is happening. And after a while, what's happening is that there's some impurity at the boundary, and at the boundary you generate a nucleation, and this is sort of propagating into your cell. And after a few seconds, I mean, the cell is totally black. Okay. So this is of course not what you want to have for your experiment. You want to have sort of a controlled initial condition, and the controlled initial condition is, I mean, the simplest one which you can do is the simplest one you can do is you take a strong laser pointer and just point it into the middle of your cell, and miraculously this laser pointer sort of this is metastable. What the laser pointer will generate is sort of it will nucleate the stable phase, and then this is sort of going to sort of expand into all directions. Okay, and so you see that the easiest thing Takeuchi can generate is actually exactly this situation. And then, of course, he knew about all these results. I mean, he was eager to also test the other things, and I will not go into them at all. But I just want to say that beyond this, of course, now you can imagine that you take your laser pointer, and you tell your laser to make something like this. And so now you nucleate the flat initial condition, and then of course this is expanding in this way and this way, and now you have a realization of the flat initial condition. And the random initial condition, he worked for many years. It took him with associates, and in the meantime he had a bigger lab, and anyway, so the random was very complicated, and the reason why the random was very complicated is that he had to tell this laser to make sort of like a random walk here, and it had to be on the right scale. Anyway, but eventually he succeeded also for that case. All right, so now. I want to, so maybe I didn't say what the experiment is. So the point is that he can repeatedly, many times, I mean, not a million, but let's say 2,000, few thousand times, he can sort of produce these initial conditions in a controlled way. It will be metastable, then he shoots with the laser, he waits, and then of course he simply measures, I mean, you can see, the boundary of the metastable phase, and so he would simply record, in a digital way, what is sort of the location of the interface, and then it just repeats, and then from this he can figure out, what are the fluctuations of the interface, right? So that's, and then sort of, typically, he has a few thousand samples, and of course, you can average also over directions, and so you have good statistics, and so all the kinds of which you're telling you, can be extremely well confirmed, because he has a controlled way and can repeat sufficiently often. Okay, so now I'm coming to the sort of more theoretical part, why this is sort of an exciting development. So let's see which way I'm doing here with time. Yeah, okay. Okay, so let me just sort of get a little bit more space here. Okay, so now the other development is sort of the 7.3. This is the exact solution. And so I will spend, presumably for the rest of the lecture, quite a bit of time on this exact solution. Now, of course, I cannot go into extreme details, but I sort of want to give you at least sort of some sort of feeling of what people have done. So the initial work was done by probabilists in Sweden, in Stockholm, Kurt Johansson. So this was 2000 when he discovered that, and I mean, the reason why he even looked at this problem was sort of a different story. Maybe I come back to this at the end, but now at the moment I just want to concentrate on this case. And so what he somehow realized, that for some reason the simplest case is what people call the corner growth. And so you look at the TARSEP, and you have this corner here, and you have some fluctuating interface, which is sort of constructed the way I showed you by just randomly adding xi squares. And then you want to look at the, so this is the origin, so these are my j's. And you basically just look at the height at the origin at time t. So this is the quantity which you can sort of, in terms of exact solution, that's the quantity which is most easily accessible. And now let's see what is happening. Well, I mean, one thing we know already, you see, remember that we do step initial conditions. So this is our TARSEP initial condition. And then I told you that, this will spread out. Here the left density is 1 and the right density is 0. So for sure, I mean, we'll spread out like this. Okay, and we are sitting right in the middle, right? I mean, so if you integrate this, I mean, you will see, you see that the macroscopic shape will be simply a parabola. So it's a parabola. So maybe I should plot the macroscopic shape here. I mean, this would be a better indication. So then this fluctuations are actually not so good. I mean, so let me first plot the parabola. So this is the parabola, which is sort of touching on both sides. I mean, this just comes from the solution of the TARSEP, but now we are looking at fluctuation scale. So then of course, this is not contained in this picture, right? And so the actual interface is lagging a little bit behind. So this is the fluctuations. Okay. All right. So let's see what we can say. So. Okay, so I was wanted to write down the formula. I mean, so I look at h of t equals at the origin at time t, and okay. So the first thing is obvious. I mean, we know how this is moving. I mean, it's just sort of it's always the same shape, but will be proportional to t. So and then I'm density 1/2. So here the current will be 1/2, and then whenever I add a block, I mean, then the height is increasing by 2. So eventually there will be 1/2 times c, if I did this correctly. Okay, so this is what we get from the macroscopic equation, but of course, no information about the fluctuations. And then the result of Johansson is that there's some. Okay, let me first write it out. I mean. 1/3, and this is some time scale, and this is sort of model dependent. Of course, for the TARSEP, it's one fixed number. But when we think about the experiment, then the first thing what he does is he would actually try to figure out what is the gamma. Now, again, I mean this requires some theory, but the point is that of course the gamma depends, on the particular sort of experimental situation, and then if I do another model, if I do rather than doing the TARSEP and do the RSEP, I mean, I will different gammas. So this is model dependent. But the quantity which is not model dependent is a fluctuation quantity, which I call here TW, and this is called the GUE Tracy rhythm distribution. You see, I know nobody knew about the Tracy rhythm distribution. Tracy rhythm is 1983 or so. Nobody knew about this Tracy rhythm distribution, but now you can find it in Wikipedia, and then sort of people are very happy about it. Okay, so what is this is a random quantity. It just tells you how these things are fluctuating. So in the case of what we discussed before, I mean these fluctuations were always Gaussian, but this is something which is non-Gaussian. And that's, of course, one of the reasons why people were interested in, because, I mean, central limit theorem we have seen for a century, but if you see something in a natural sort of construction and suddenly something non-Gaussian appears, I mean, that means that there must be something sort of exceptional going on. And so what does this function look like? Well, it's sort of not so difficult. I mean, so it's actually a function. Well, maybe I erase here. So now I'm plotting the probability distribution. So you can think of it sort of like a somewhat deformed Gaussian, but and of course it's very much deformed. I mean, so first of all, so now I'm plotting this psi, and here I'm plotting the probability. So I'm probably plotting the probability density, and so it look something like this. Okay, and so it has skewness. I mean, it's certainly not symmetric. I mean, which is clear because our situation is highly asymmetric. I mean, fluctuations away from the deterministic are very different than fluctuations towards where you see lots of particles. I mean, so it's not so surprising. And then you have sort of you have some mean. I mean, there's the mean which is also universal, which people sort of were very much surprised about. Usually the mean is sort of something which depends on your experiment, but here the mean is actually also universal, and you can actually measure there's a very precise prediction on what the mean should be. I mean, the mean is something like minus 0. whatever, 2 or so, and so there's a very specific prediction you can actually verify. Anyway, so you have two tails. I mean, this goes like e to the minus x to the 3/2, I guess. Yeah, so x to the 3/2. In this way, you have an e to the minus x cubed behavior. Okay, so the tails are also asymmetric because here, the motion is much more restricted, and therefore it sort of decays faster. Whereas here, you sort of somehow fluctuate in the vacuum, and therefore, okay. So here is the vacuum, and here is the plus phase, right? Okay. Now I want to write down for you a formula. Not so much that you're impressed by the formula, but just to tell you that it's an exact solution, but and sometimes you have exact solution is given in terms of elementary functions. And I want to write down for you the exact solution so that you understand that there is something sort of more difficult going on, right? And so here's the formula. So I'm writing down the not the density, but what people call the distribution function. So I look at the probability that this is less than s. I mean, so it would be the integral of this object. I mean, which would this is normalized to 1, and so for large values, I mean, this will go to 1. And the point is that this can be written as a determinant, and this I want to explain a little bit. I mean, so it's 1 minus. I'm going to explain the symbols in a second. Then there's. So P is not a probability. Okay, so maybe I should have put here. So this is a probability. Okay, so these P's are projections, actual projection operators. Okay, so then there is. And now, I mean, for the determinant, I would not have to put it, but it's nicer to have a symmetric operator. Okay, so let me just go through one by one. I mean, first of all, what you have here is, like in quantum mechanics, I mean, these are operators which are living on the real line, and the easiest which I can, I mean, these are even simpler, but I mean, the easiest which I can, which is what is called the Airy operator, which is a quantum Hamiltonian, which has here the second derivative. But then Airy comes from the fact that, the eigenfunctions of this operator are the Airy functions, and then you have here a linear potential, okay? So this is one of these, quantum mechanical problem which you can solve exactly, and which has sort of interesting properties. It's just a particle sitting in the linear potential, right? All right, so this is the Airy operator, and so you see that these operators are living in a Hilbert space, which is the real line, and of course I use dx as my volume element. So okay, and the p as infinity is simply the projection onto the interval as infinity, right? I mean, so all what I do is I take some function psi, and then if I do this PS, I mean, then what I have to multiply is with x, the characteristic function for x larger than s, and then it's the same function psi. So this is a very simple operator. It just takes the function and simply cuts away everything which is smaller than s. Okay, so you have now an operator which is a product of three projections, right? I mean, okay, and now you might wonder what is the determinant. Well, I mean, the determinant is just like for a matrix. I mean, this is a self-adjoint operator. I mean, you have to do a little bit of thinking, and you realize that because I put this S projection, this of course is unbounded, but here you will have eigenvalues, and I mean these eigenvalues you have eigenvalues, and so the determinant the determinant is nothing else but the product of the eigenvalues, right? I mean, this is so these are eigenvalues, right? I mean, so I'm just saying that this determinant is well defined. Eigenvalues. And so you see that if you want to actually produce plots, I mean, then I mean, one way to do it is to sort of numerically evaluate this determinant. I mean, you do the obvious thing. I mean, you put a grid, and then you sort of write this as matrices of size maybe 1,000 by 1,000, and then you do Mathematica, and then it will sort of produce for you the eigenvalues, and you can compute the determinant, and then you have to study this object, as a function of S, and then you will get a plot like this. Okay. Actual fact, again, there's an amazing sort of technology behind how to actually really get very good plots. I mean, if you do this, I mean, then you get sort of a rough shape which sort of looks like this, but you will not get a very precise plot. I mean, so there are many numerical tricks behind doing such kind of things, and okay, so it's not important for our purposes here. Okay. All right. So this is sort of number one. So it's just sort of indicating that this distribution is sort of a somewhat more difficult object than sort of, let's say, a Gaussian distribution or other sort of distribution which you are familiar with. Okay. Then the other thing which so I have to look at my watch. I mean, what I'm doing here. Yeah. Okay. So the other thing which I wanted to explain. I mean, how come? I mean, why would Tracy Whittam in the early 90s even look at this problem? I mean, they didn't know anything about Tarsep or anything like that, right? I mean, so why would they even look at this problem? Okay, and the reason why they studied this, and why they actually their formula was different, but it's equivalent to what I'm writing here. What is the problem they wanted to solve? And lo and behold, I mean, and this was sort of part of this 2000 revolution, that people realized that this Tarsep, which of course people had studied before, has a connection to a field which is in some sense total or orthogonal, but through this simple model it sort of becomes connected. So they were actually studying a random matrix problem. Which of course is I mean a lot. I mean people I mean random matrices are everywhere and studied for all kind of purposes, various areas of physics. But let me just tell you the one which they did. I mean, which is sort of something which is called GUE, which was originally introduced by Wigner as a simple model for the excited states of a nucleus, right? I mean, so you see again, this idea that you have a complicated physical system. You somehow still want to do modeling, and then you sort of consult and do a stochastic model, right? It's the same feature which sort of reappears. And so what is this random matrix which he proposed? Well, it's rather simple. I mean, you basically say that you take an n by n matrix. Okay, and now you fill this matrix elements simply with Gaussians. Now you see, you want to have, I mean, the GU means sort of whatever, invariant under unitary transformation. So you want to think of matrix elements which are actually complex, but the matrix itself should be symmetric, right? I mean, so actually, what you plug into the diagonals, into the matrix elements, are complex Gaussians, right? I mean, so this is a two-dimensional Gaussian distribution. I mean, or let's say an independent real and imaginary part, right? And so if I write down a formula, I mean, you take Xij to be a unit complex Gaussian. So this gives you a probability distribution of a number in the complex plane, and then you define your random matrix A, Ij. Well, I mean, you just do. I mean, you want to make it self-adjoint. I mean, so and then you take here the Hermitian conjugate. I mean, so or maybe I can even write it like this if you want. So Ji and your complex conjugate, right? I mean, so this is the definition of this random matrix. And it's what people call a fully occupied matrix, right? I mean, you see, you have all these matrix elements over here, and all of them are random. I mean, you know, very often we have matrices which are nearly diagonal or so, but that's just sort of totally opposite of that, right? And now for more pedagogical reason, I multiply this with, let me see, I have to do this correctly. I multiply, so these are unit Gaussians. So if I take absolute value squared, I mean, then this will be equal to 1. But I want to multiply this with square root of n, which is sort of only emphasizing the analogy between this problem and the problem which we are studying. Okay, so now we want to study this problem. I mean, this is a problem which of course people knew. I mean, this was around since Wigner and Dyson and other people sort of looked at these problems. So you know, it was was a very well-known object, and of course one of the things, I mean, whenever you have random matrices, I mean, what do you want to do? Well, I mean, you want to say something about the distribution of eigenvalues. I mean, you know, what else should you do? Okay, so you look at the eigenvalues, which of course are also random, and in my units, I mean, the way how so here I'm plotting the eigenvalues. And again, you know, you have this separation sort of into mesoscopic scale and microscopic scale. I mean, what Wigner knew already that you know, if I have large n, then these eigenvalues will have a density which is exactly a semicircle. Right? So you know, you have many eigenvalues sitting here, make n large, and then eventually it will go to a deterministic shape. And for this and many other matrices, you know, it just goes to a semicircle. So this is the Wigner semicircle. Now maybe you want to look on a finer scale, and well, I mean, yeah, of course you could look here maybe at a finer scale. I mean, that's something you can do. But I mean, what Tracy Widom wanted to do, you know, they sort of were enlarging this piece here. So somewhere you have the edge. So the edge actually in my units is at 2n, right? So here you have the edge, this is 2n, but then you use your microscope, and then you will see, of course, the discrete set of eigenvalues, so somewhere over here, maybe this one, and then maybe others. And now they decided to look, what is a rather natural question, at least mathematically, they decided to look at the largest eigenvalue. Okay, so you know, the largest eigenvalue sits typically a little bit to the left of the edge. Okay, and then let me call it lambda n. And then you know, their theorem was that lambda n is equal to 2n, and then n to the 1/3. And then they found this distribution, and it's the Tracy Widom distribution, right? I mean, this is why it's called Tracy Widom. I mean, they figured out that there are fluctuations of size 1 to the 3rd, and you know, distribution. And you see that this formula is sort of essentially, you know, the same formula as this one, I mean, the only difference is that the parameter T is now the size of the matrix. All right. So now I wanted to. Now, of course, I cannot go into anything at all, but I want to sort of show you one way, to give you some feeling, how you even sort of, I mean, how do you ever get such kind of exact solutions, right? And so there's one way, which we sort of discovered at some point, which sort of looks like, the easiest context how you can explain this. And so this is section number 4, and that's the so-called poorly nuclear growth PNG model. And the reason why I'm sort of introducing this model is that in this model you can sort of at least get a vague idea of how one actually would get any one of these results. Okay. So we go back to our global. I mean, as I said, we're not going to away from the models which I had originally, but now we want to sort of do a somewhat different initial condition. Namely, now we decide to do the initial condition like this. So this is plus, and this is minus. Okay. Now that's not such a clever initial condition because nothing can move. Right? I mean, according to my previous rules, I don't want to break bonds, but nothing can really move. Okay, so but now we say, okay, all right. I mean, we want to make this stable and this unstable, and so what might be happening is that at some point, I make a little sort of, succeed. Of course, out here, the probabilities are even more suppressed. But at the boundary, I might be able to sort of turn one spin, sort of flip one spin. Now you see, once I have flipped the spin, then things are very nice because then I can just keep going like this, and I can keep going like this. Okay, and this will be then, so to speak, a fast process. But then, once in a while I have this first layer, and, maybe I put another one over here, and then the same thing happens. Okay, and so the PNG model is sort of an idealization of this type of what we call. It was not invented by us. The nuclear growth is sort of a rather natural. Well, I'll show you a picture. So originally, the nuclear growth was the idea that you sort of in the plane. You put sort of randomly nuclei, and then they start sort of expanding like this, right? And then, of course, at some point, these circles sort of overlap, and then you get the first layer, and then the third layer, etc., etc. So this was the original physical model, which is rather natural. But here we are sort of doing the one-dimensional version of that model, right? And so what are the two moves which you have? Well, first of all, you have this deterministic moving of the edges. So if I have a down step, then this will move this way, and if I have an up step, this you can see from this picture, right? And then it will move this way. So this is certainly one important. So all the steps will move with velocity 1. And well, what else can happen? Well, you see that I might have sort of created another thing over here, and then this is moving this way, and this is moving this way. So at some point, they will simply coalesce and will form a layer. So this means that you have plus coalescence. So then out of this step, you're making simply this one, right? So whenever a down and up sort of this is a down and up are joining, then they simply complete the layer, and that's it. Okay, and then of course you have this random nucleation. And they of course they are totally random. Whether it's nucleated over here or here is sort of question of luck, and therefore the other thing which we have is the following process. Maybe I can put it over here. You have sort of some piece of this stepped surface. So maybe I should plot now also the H surface. So this is now X. It's actually this has become a continuum, and here's the height, and then now the height is simply, in discrete step, right? I mean, so the surface looks maybe like this, etc. Right? And so what I'm saying is that at every surface, you might randomly nucleate an X peak, so to speak, and of course, this is, so to speak, an upset downside, and this is sort of moving this way, right? And this is sort of like a random thing. So if this is the current surface, then maybe I create another sort of nucleus over here, and then this nucleus will sort of spread in this direction, and then of course they will coincide, etc., etc. Okay. All right. So this you see, I use many words to explain something which is very simple, and in fact it becomes even simpler if you think for a second about how would this process sort of look in space-time? I mean, then I think what's going on is even more intuitive. So okay, now maybe I haven't said one thing. So you see, we want to be, in the case of the step initial condition. I mean, so we want to have sort of like sort of like here. I mean, like a droplet shape, and this is easy to form. You see the way how you do okay. So maybe I first let's see. Yeah. Okay. So let's first do the droplet. The droplet you do by just imagining that you put a ground layer, where this is a time t, and it's sort of moving out with unit velocity. And the rule is that out here you simply are not allowed to nucleate, but you nucleate on the first layer, second layer, etc. And when you look at this, then asymptotically, I mean, you will see. In fact, you will see sort of like a semicircle, right? Because you can more nucleate it at the center and a little bit less at the bounders, and this is sort of moving out linearly. Okay, and so now I want to just plot for you the space-time picture, which is even more intuitive. So I start with with this kind of boundary condition. So this means that I have this cone here. So this is the light cone, and by phi, I assume that nucleation can be only inside the light cone. Okay, and so maybe over here I have my first nucleation event, and then I'm plotting, the right and left going edges. So this will go this way, and this will go this way. Okay. And then maybe I have another nucleation which is sitting over here. And of course I have right and left, and then I keep going, and then you see at this point they just annihilate, right? I mean, that was this event. And so here, this simply stops, but they just keep going. Well, then I have maybe another nucleus over here, and this will go like this, and this is sort of the time t where I do my observation. Okay, and so you see that as I continue this, then I can figure out what is the height. I mean, this, I'm the first layer, so this would be the height 1. Now all this corresponds to height 2, and this corresponds to height 3. And so if I do this kind of thing, then you see that at time t, I give you some random configuration of these nucleation events, and then, for this very particular initial condition, I do this graphical construction, and then at time t, I can sort of see so here would be height 1, and then I have here 2, 3, 2, 1. I mean, a simple configuration, but, you can think about more complicated things. All right. Okay, so now why is this useful? And now comes sort of the miracle. So I cannot really explain in more detail why it really happens. I mean, so you, yes? You mean from here to here? No, okay, so the first thing is I'm plotting the light cone by saying that outside the light cone I have no nucleation event, right? So this produces the droplet shape. And then I'm just saying that, in my space-time world, I have nucleation events randomly. So I put 3 points, right? If I make time even larger, of course I will more. And then they are just, uniform density. I just take random points in that light cone. Okay, now once I have given you the nucleation event, I iteratively construct the the surface. And to do this, I have to sort of really move in time, right? So I go up here and I look at the first. So okay, I first sort of, I mean, it's clear that for a very short time, this will go this way and this way. Okay, so I go up and then go for the first time, but then I have to be a little bit careful because at some point these two lines might cross and then they annihilate and then they are sort of disappear, right?
Each nucleation takes
Yeah,
their own life.
yeah. But of course, since I'm constant, I mean, I have a uniform density of these points, so I will, will never die out completely, right? I mean, that would be a very unlikely event. Okay, and eventually I will get some random surface up here.
Sir,
Yes.
sir, should the slope always be the same? Because during the expansion, like horizontal expansion.
Well, they all move with the same velocity 1. I mean, the speed of light is 1.
Yes, sir, but it's not necessary that it should expand horizontally at every
Yes,
time.
that's the model. I mean,
Right.
this one is moving with velocity +1, and this is moving with velocity -1. And all these things, all these things are moving with the speed of light.
Yes, sir, but there is no energy, it's not energetically favored, right? It's just neutral, like when it expands horizontally. So,
Yeah.
right. So it can happen that in a time step it doesn't expand horizontally.
No.
So,
No,
okay,
it
the
cannot
model is
happen.
like it should
No,
expand.
they always move. I mean, here you can see this in this picture. They always move with the speed of light.
Right, okay.
They all have, all these objects have exactly the same speed. Always the speed of light. Okay?
Right, yes,
And
yes.
then all what can happen is that once in a while I create a pair. One is just going to the right, the other one is going to the left. And then once in a while what can happen is that the pair annihilates.
Yes,
And that's it.
yeah.
Nothing else is happening.
Right, okay.
Okay? In this model, of course, in the real world, something else is fortunately happening. But in this model, nothing else is happening. Okay? All right. Okay. So now I wanted to tell you what is sort of
Herbert,
yes.
what is the probability of the random nucleation? I think I missed
what
you.
was that? Yeah.
I think I missed you when you mentioned the probability of random nucleation. I mean, 1 and 2 will form, they will annihilate, but how do we know that, like, what is the probability of the third nucleation to happen, like on top of the first layer?
Well, it's the probability of having a Poisson point at that location. Which
A
is
po-
0.
okay.
No. Look, I mean, these red dots are just random points which you put initially, right? I mean, you can sort of imagine that, I want to go all the way. So here, I just take an ideal gas and I just put, 10,000 points randomly in this triangle.
Okay. So
And I do
it's
this with a
okay.
constant density, right? I mean,
I
so,
got it.
as I go up, there will be more and more points because, there's more volume.
Yeah.
It's just random points.
Okay.
All
Thank you.
right. Okay, so now comes the miracle. So I just want to explain you the miracle, and then I'm sort of out of time anyhow. Yeah, that just sort of works very nicely. But the miracle I would like to explain you. Okay, and this is the miracle is the following: that out of this thing, which, I mean, this is just to visualize it a little bit better what's going on. It's sort of a space-time picture of how these steps are moving, and it's also sort of geometrically sort of very appealing construction, so that's fine. But the miracle comes by looking at what we call the multi-lane representation. And you see, if you want, so it's somehow recording all this information in a somewhat different way, which at the first sort of you would not think about it. I mean, what I wanted to say is that as I go up, and if I just look at the height, then I'm losing information. You see, I don't really. When you look at this construction, I mean, you cannot sort of, if I just only give you the height function, I mean, it's not so easy to see where these individual points come from. And so what I do in this representation, because when they annihilate, I mean, they sort of hide some of their past history. And so in this representation, I want to sort of keep the entire information about sort of the location of the Poisson points. And the way how you do this is that you introduce the following step. I mean, so maybe I have, I just have to do some examples. I mean, so I do this kind of thing. Okay, so let's say this is a particular part of my surface, and now this is moving inwards, this is going away, and this information is lost. I mean, it might have come from other things which also annihilate, and I don't really know at what point they have sort of, disappeared. Or what I see at some later time is just sort of the flat surface, right? I mean, so I don't know where this actually was sitting. Okay, so in order to keep this information, I keep a line below. So here's one line, here's another line, here's the next line. And I record this disappearance as a nucleation on the line below. Okay, so what I'm going to do is that after a short time step, I have the same picture. Okay. Okay, it's the same thing. Okay, so this now has disappeared, but it has so this goes to zero, so I don't see it anymore. But of course, at exactly the same moment when they sort of annihilate, I put a nucleation on the line below, and this line below is now expanding in these directions again. And so you see, and then now of course then I'm still losing information. I have to put the next line, and I have to put sort of all the lines down, and then I don't lose any information whatsoever. Is that fair enough? Okay. You see, whenever this annihilates, I'm losing, because I just see the line. I don't remember, at which, I don't remember where actually this nucleation event, which is behind it. I mean, where this annihilation event, where this exactly happened. But now I'm recording the annihilation event as a creation event on the lower line, and therefore no information is lost. Okay, and from this you get now the multi-line ensemble, which looks like this. Okay, so here I have, let's say, level 0. And I'm starting with this flat surface. So this construction is done for a fixed time t. I mean, the t is now the time t is basically this width. That's 2t maybe. Put here some middle. Okay. Okay. At the initial time, I just have an empty book, so to speak, with a lot of pages. I mean, so here's the first page, here's the second page goes all the way to infinity, and this sort of is my recording device. Okay, and now I start moving the first layer. I mean, that's sort of the one which I have over here. I let it grow up to time t, and then I do all this recording, right? And so what you're going to see, I'm just going to make a simple example. I mean, so this of course has none. So this is moving according to my PNG thing. Okay, so this is moving to the PNG. So maybe I have this thing, right? Okay, but then now this one has recorded something. So this has another step, and maybe another step over here. I'm just doing now a fantasy picture. I mean, so okay, and then there will be some recording over here. Okay, so but now of course eventually, the lines will become flat because I cannot record more than I have this kind of nucleation events, right? And so the picture will be this kind of line ensemble. Okay, so now I have done this recording. Now, of course, it would not be of much use. It's just sort of another picture. But now comes sort of the interesting observation is that you see, this comes with a particular probability because it comes from this growth process. But now I'm saying that forget about how it was obtained by the growth process. Let's just imagine, what would be the statistic of these lines. And it turns out to be a very simple statistics. Namely, all what I have to do is I have to put random lines. Now, what do I mean by random lines? That's sort of not immediately obvious, but let me sort of explain this for a single line, and then you will understand how you to do this for many lines. So for a single line, it's very easy. You see, I pin the line at both ends, right? I mean, so, and then I have now such a random line. Let's say like this, okay? Now, how would I sort of even label this line? Well, you know, I label, let's say, the up step. I mean, this is y1. Let's say plus y1, and then the down step would be y1 minus, and then there's another one, y2 minus, and then there's an up step which is y2 plus. And now, what I mean by random is that it's just uniform distribution. The usual uniform distribution, but of course under the constraint which I've given you here, right? I mean, so I mean, for instance, you know, they have to, you know, there must be this kind of inequality, etc., right? I mean, so you know, this is what I mean by random, you know, under the natural constraint, and the same thing over here. You see, I mean, you know, you can see this geometrically. You know, there's a constraint that you know they should never overlap, right? I mean, so. Here the constraint is that, you know, eventually it has to come back to the point. And, okay, so, but up to that, it's sort of completely random. All right, so this is something which you, okay, so, and now you, okay, so the big observation is that once you make this recording and you do the multi-line, then you get for the multi-line, in some sense, you know, the simplest possible statistics. I mean, except for the constraint, everything is random. And so if I would take a single line, that of course would give me just an ordinary random walk, which is conditioned, you know, let's say to start at some given point and to end up at the same point going for time 2t, right? I mean, this time was 2t, right? So it would be just, if I do a random pass, I mean, and just put all the steps up and down sort of completely random, that's nothing else but the ordinary random walk. Conditioned to come back to the same point. All right, so now you have to remember your quantum mechanics. And when you remember your quantum mechanics, well, anyway, so when you remember your quantum mechanics, then you understand that, you know, this kind of picture sort of is familiar, but now, so this time is sort of a fixed parameter, but the quantum evolution will go this way. And so the quantum evolution will have points sitting over here. So these are my fermions, and up here it's totally empty. So here there's nothing. But at time 2, the time evolution will sort of return to this configuration. And the quantum Hamiltonian, the propagator of the quantum evolution, will be going from this line to this line. And, you know, because everything is random, what the quantum evolution is that it's simply a free fermion gas. And so now I'm just sort of assuming that at least some of you have heard some course on many-body quantum mechanics. So just let me write down, you know, the Hamiltonian, which presumably, you know, you did a lot of exercise on. So you know, the physical space is now this lattice, right? I mean, so I have creation annihilation operator. So it's just the usual nearest neighbor hopping, right? Now it requires a little while to sort of understand this, but you know it's nothing very original. I mean, Feynman and these people understood this already. Okay, and so what I'm saying is that the propagator which you actually have is e to the minus. Let me call it with a different parameter. I mean, let's say tau h, right? And so let me do this a little bit over here. I mean, I understand what I want to do. So now I'm turning things around. And so now I have my free fermion gas over here. This is J, and I'm studying a very particular initial condition, namely, you know, I want to start with to the left everything is occupied, and to the right everything is empty. And now I start propagating with this thing. So, you know, I'm propagating with my wave function psi. The wave function is just a pure state. I mean, it's just to the left, all occupied, empty. And then, you know, I come up to time 2t. And of course, you know, it's constrained to see the same configuration, right? And of course, this has more probability, but then, you know, when you normalize, it's the usual thing that you know, when you do statistical mechanics in equilibrium, I mean, you write down a Boltzmann factor, and that, of course, it's not normalized. If you normalize, then you get sort of decent things. Okay, and so this one is all empty, right? Okay, and so now the time evolution is going this way. And so maybe from the other side, you want to have the same state, e to the minus. Now, the total time should be 2t. I mean, so maybe I can also put here the t, right? And then I put e to the minus t. And then maybe you want to know some probability. I mean, so for instance, I want to know whether you see when I look here in the middle. So now I done a propagation sort of into the middle. I mean, where my observable is going to be placed. I mean, you want to know whether as I'm looking over here, whether I see a particle or see no particle, right? I mean, so you want to compute an expectation. Let's say you want to compute here the A dagger HA. Okay, and so now what I'm saying is that you know, going through this step, eventually I have a formula. So, for instance, I can ask myself, what is the probability that you know, the PNG height is below a certain level? Okay, that just means that in the fermionic gas, I must compute what is the probability that above this level there is no fermion. And so this would be sort of like the average occupation at ladder side J. Okay, and once I have this fermionic expectation, I can sort of compute quantities which I really want to know, right? I mean, you know, this is just sort of in order to get a representation which you can use for computations. And now I remind you, so the fermionic K vector is reflected by the fact that these world lines can never touch. Right? I mean, if I would do the same thing for bosons, I mean, then of course I would get a different world picture. Okay? So this is okay. So the world lines. Just a moment. I mean, so maybe I should put this more precisely. So these are the world lines. So this is Euclidean, right? I mean, you know, I mean, I'm not doing. You know, my propagator is not e to the minus ith, it's e to the minus th, right? I mean, so I'm using it's already done after equation, right? Okay, now comes the question.
So this expectation finally gives the probability of a particular surface.
I mean, this particular would give you the probability that. So I'm looking at this picture, and can I ask myself? Okay, I'm looking at. Okay, so you see here, I'm looking in the middle because I mean this I put the same thing. So I'm sitting here, right? And I could ask myself, yeah, let's say, okay, so let's say I look at j equal to 0, then this would be the probability. I'm in the middle because I put here t and I put here also t, right? Okay, so this would be the probability that in this line ensemble I see a line at the origin. If I put 0, 0 index, so let's do it very concrete. I mean, so I put here 0, 0. This is some number, and this number tells me what is the probability that at this point I see a line. And if I go to some other space point, I mean, you have to adjust, right? I mean, so of course it gives you the full probability everywhere, right? And of course, you have to do more work in order to get, you know, finally to this crazy rhythm, which I'm not going into at all. I just wanted to explain to you why, you know, when looking very carefully, you realize that you know, the exact solution is on something which is sort of extremely well known in equilibrium statistical mechanics, namely that you're saying, you know, this is free fermion, and therefore I can lose it. The two-dimensional Ising model is free fermions, right? I mean, that's something, but But the fact is that now it comes up in a dynamical problem in a very sort of somewhat convoluted way. And also, it's very different from what people use exact solutions, let's say in the Ising model. In the Ising model, you use very heavily that, of course, your model is translation invariant. Here, there's no translation invariance whatsoever. You see, I mean, I'm looking at the state, which is already sort of not translation invariant. And so, wherever I look in space-time, I mean, it's inhomogeneous. But nevertheless, I mean, having free fermions is such a powerful tool that, you can deal with this situation. Okay? All right, so this is the end of that part. And now I want to sort of explain you one other thing, which now it's sort of more pictures and no formulas anymore. In fact, Johansson was not studying this problem. He was studying a different problem. And again, it's this somewhat surprising connection between Quo's processes and other type of problems. And so maybe, I don't know, I guess I put another section here. Has disappeared here. Okay, has disappeared. Anyway, I mean, it's not so important. Anyway, so it must be somewhere here. Anyway, no, here I put all my papers. Okay, so yeah, okay, so this is what I wanted to say. Okay, so maybe okay, so yeah, maybe I should put actually sort of another section here, whatever, 7.4, and then this is tiling. So actually, Johansson was looking at the tiling problem. But it's sort of, in spirit it's the same. So let me just stop by talking on a little bit on the tiling problem. This is now equilibrium, but the point is it's similar like this thing. You see that, of course, this is sort of a statistical mechanics problem, but the original one was clearly, growth of a surface. I mean, so this was clearly a dynamical problem. It's just the point that you can map one to the other, and then very often if you sort of put it into the statistical mechanics language, I mean, then you have maybe tools to solve it. And so I just want to explain you what Johansson was interested in. So you do the following thing. I mean, you do a tiling, and it's domino tiling. I mean, so you have just these two things. And then you have here whatever, n by n. And then you want to randomly put the tiles, okay? All right, so this is a nice statistical mechanics problem, so you can sort of study this, and whatever densities, you can think about correlation functions, and et cetera, right? I mean, so that's fine. Okay, at that point, you would think, okay, I mean, so what's the point? But now it's sort of the usual thing that you make a small twist, and you get suddenly to something which was sort of, first of all, more fascinating, for which you not immediately have any solution. So let's say, why don't we do the following? I mean, so why don't we simply turn this by 45 degrees? I mean, so I start with here, and then I go down here, and then I go down here. Okay, so I have to go here. Oh, well, okay, so anyway, so let's see, 1, 2, 3. Okay, so. Okay, so this is a bad picture, but all what you should think is that I turn this by 45 degrees, and then now, of course, I get. I mean, this line is sort of oriented at 45 degrees, right? And now you see that I mean, the tiling becomes a little bit more complicated. But I've carefully drawn, that here I can put a tile, and here I can put a tile, and here I can also put a tile, and here I can put a tile, right? I mean, so in some sense you would say that making this of length 2 somehow refers to having tiles oriented at these 4 corners. And now you do exactly the same thing. You make things large, and then the question is, what are you going to see? And the point is that now you're going to see some interesting behavior. I mean, so on a large scale, of course, it will be just something like this. Okay, then you have an inscribed circle. Okay, and what you see is that that out here things are perfectly ordered, right? I mean, basically, they remember that here I started with this ordering, and then it's sort of preferential to keep that order also at the next stage, right? I mean, you put the first domino, and then you put the next domino also like this, and then it's just like here. But then eventually you forget, right? I mean, so you cannot do this forever, and so you see that these things are ordered, and here they are disordered. So here, they look a little bit like what you would sort of would see in this thing with periodic boundary condition. So here, they're just sort of randomly, but out here they're sort of perfectly ordered. And so what Johansson actually wanted to study was the question: what about this? Let's say, what about this line here until it touches? Now you see. People knew already before that this will be just sort of a circle which touches the boundary, but now of course I mean where the ordered zone stops is perfectly defined, because whenever you start to make errors, I mean this is sort of the edge. So he was interested in understanding the fluctuations. And of course, he had no idea about these dynamical problems. And so, they came from a totally different direction. And eventually, everything combined, I mean, this was sort of then later development. But his sort of beautiful theorem, which sort of started much of this sort of probabilistic activities, was that he was doing actually something very similar. I mean, in this thing, I mean, he sort of constructed a line ensemble which is a little bit more complicated than the way I had it, and all the kernels which appear there. And from this representation, he was able to prove that the line actually fluctuates according to tracy rhythm. So the answer is that, again, I mean, you have a linear term, and then you have an n to the 1/3 term. So this edge is fluctuating like n to the 1/3, and then you have the tracy rhythm. Right? So here he made no connection to KBC. I mean, but eventually everything sort of was put together, and so one can see that which was in the sense of surface growth is sort of a dynamical problem of how these things is expanding. Has sort of percussions towards tiling and other things. Okay, so maybe that's a good point to stop, and thank you very much for listening.
I had two questions. One was regarding here you see in the height fluctuations, you mentioned that it's a tracy rhythm. But if you talk about rare events of the largest height at, let's say, origin, is that also tracy rhythm? For example, in log gas, I mean random matrices, rare events are not described by tracy rhythm at the edges, right?
Yeah.
What happens in the case of?
Let's see. I mean, okay. So I think I mean, so you're asking sort of semicircle law, and then one is saying that the eigenvalues at the edge, I mean, will be tracy rhythm. And now you want to know what is the eigenvalue in between? Is that right?
No. Of the largest eigenvalue.
Yes.
Having a very small value. In a sense, like rare events of the largest.
So this is the largest, and then you have done this one, or?
Just push the largest eigenvalue towards the bulk. In a sense, what are the atypical
okay,
fluctuations?
So just to understand the question. So this is my largest eigenvalue. Then, of course, if you enlarge according to what I said, is that you of course you will see a next eigenvalue. Yes. And
without seeing the next
of the same order away. This one was n to the 1/3 away. I mean, the next one is also n to the 1/3 away.
No. Sorry.
Why don't you show at the blackboard? I mean, what you want to?
No.
Which eigenvalue you want to know? I mean.
I'm talking about the.
I guess he's asking the distribution of the largest eigenvalue is tracy rhythm.
Yes.
But if you ask for the
Oh, the large deviations, what you want? Ah, okay. So you ask, yeah, no, okay, yeah, the people have studied that also. That's right. Okay, okay, so I didn't understand the question. I mean, okay, the point is that you know, okay, so let's forget about this. I look at the largest eigenvalue. What I'm studying is sort of what you would call the typical fluctuations of that eigenvalue. Right? And here the question is whether you can ask, you know, what is the probability that this eigenvalue is very, very far out, right? I mean, yeah.
Yeah.
Yeah, people have studied all. I mean, this is a well-studied model. I mean, it's also free fermions, and whatever question you can do. I mean, you know, of course, some of the questions are more difficult than others, but I mean, that people have done, yeah.
The motivation for the question was to understand whether that is similar to the log gas. I mean, the atypical fluctuations, large deviation function from the random matrix. Is it same as?
Well, you know,
for
I mean, here for the
KPZ?
GUE, I mean, the distribution of the eigenvalues is the log gas.
Yes. And
So then you know, if you start, I mean, the point is that for the GUE, you can write down, you know, the full probability distribution of your eigenvalues. And
yes.
that turns out to be the log gas. And so that then your question can be then also phrased, I forget about where it came from. I mean, what are the properties of the log gas? Yeah.
Actually, I'm asking about KPZ. Do you say similar things for KPZ also, or is it completely different?
No, I don't think there's no. I mean, you know, you can also ask similar questions, you know, here for the surface. I mean, you know, what is the probability of that surface, you know, to have sort of a very unlikely fluctuation? Yeah. But you see, this mapping is sort of, you know, maintains, you know, the full statistical information. So if you have such a question, I mean, you can still use the free fermion representation, and then you can see whether you can say anything sensible about it, right? I mean, yeah.
Okay.
In case of corner growth model, the dynamics was that it, completely asymmetric dynamics. Only local valleys can become the local hill. If in the corner growth model, we implement the dynamics of EW model, that is the local hill can go to local valley, and local valley can also go to local hill with equal probability.
So you want to go from you want to go from the TASEP to the ASEP, right? Is that your question, basically? I mean, you know, you want to allow not only filling up local minima, but sort of removing local maxima.
Yes. In that case, whether the distribution will be something else than GU distribution, or that will still be the same?
No. In this case, I mean, the ASEP is a much more difficult problem, right? I mean, all these mappings which I was talking about do no longer work. I mean, as a model, it's more complicated, but people know that in the ASEP you will have also tracy rhythm distribution. In fact, by now we have like 20 or maybe even more models which have showed the tracy rhythm distribution, right? I mean, so people, you know, find this very fascinating and invested a lot of work to find other models, you know, which have the same behavior. But the point is that you know what we are lacking is sort of like a more generic type of thing. I mean, you see, it's always that you do one value like ASEP, you do a particular model, or maybe, you know, you can also, I mean, you know, other models which people have used is that you know, rather than having nearest neighbor growth, I mean, or the nearest neighbor jumps in the word of the TASEP, I mean, you allow for somewhat longer range jumps. I mean, but then you adjust them in a very particular way so that you can actually find the exact solution, right? I mean, so you know, you see, you could ask, okay, so how should I say this? Yeah, I mean, you could ask, for instance, you know, that the jumps are still one-sided, but with a particular sort of, you know, jump distribution. And then for one very specific choice, you can find, you know, that it's still tracy rhythm. But of course, you know, everybody believes that you know the mechanism is rather generic. I mean, that if you make some arbitrary jump distribution, it should still be the same. I mean, such general results, of course, are not available. It's only sort of sort of linked to a particular model, and then sort of a particular technique of how to handle that model.
Thank you.
It's also, you know, the other models. I mean, which is more on the tiling side, which go in this thing. I mean, if you look at 6-vertex models, I mean, they're also in the same class. And there are many other things which sort of are connected. In some cases, one understands better. In other cases, sort of less.
Any other questions? So, yeah, so if there are no other questions, then let's thank Robert for a fantastic.
Most welcome. Thank you very much.
And I think he's still there for today's tutorial.
All right, so first of all, apologies for not sending the lectures slides in time for it to be uploaded yesterday, but I have sent it today, and I've also already sent the slides for this lecture. I don't know how much of it I'll be able to cover, because I always have this tendency. I have more slides than I can possibly cover, but nevertheless I still keep them, because somehow I always overestimate my capability to speak very fast, and I usually end up only like doing a fraction of them. But then I still keep the slides, because in case you are interested in knowing what I might have covered but couldn't get time to, you can still see those slides, and if you're not interested, just ignore them. So I don't know whether you know about this writer called George Steiner. Anybody has read George Steiner? No. Okay. So he used to be a critic. He used to write for New Yorker magazine and so on. So he has this fantastic books. He's written a number of wonderful books, but this one book that he has written is called "The Books I Never Wrote." It's fascinating. I mean, he basically talks about this, I think 7 or 9 books, which he had made plans of, but never got to write either, because it turned out to be much more challenging than he had initially imagined, or it was very contentious, and he realized that if he writes something on this, he will get in trouble and so on. But and this it's fascinating to read, like what might have happened, okay, or what he could have written about. Similarly, Stanislaw Lem has this, who's a science fiction writer, but he has this book called, I think, Imaginary Magnitudes, which is about book reviews of books which never existed. Fascinating, right? Like for example, he would review a book like a detailed study of bee culture written by Sherlock Holmes. Okay. Of course, the book never exists, but you have allusions to it in the Sherlock Holmes stories, right? Because Sherlock Holmes talks about that, he's written this treatise on beekeeping. Okay. So what might the book would have looked like? Okay. So it's a fascinating exploration of its own. So I'm not even trying to compare myself with Stanislaw Lem and George Steiner. I'm simply saying, in the hope that you see that what I might have covered had I got the time, I'm keeping those slides. So for yesterday's slides, you'll see that I didn't manage to cover hierarchy, but I have kept the slides for hierarchy there, just to show you that if you want to measure what is the level of hierarchicity of a network, like how much you can arrange them into levels, you can actually use an index very similar to modularity. Okay? Except that, whereas in modularity you are measuring how many links do you have within nodes in the same group compared to what you would have expected by chance. In hierarchy index, you basically ask an analogous question, which is you ask how many links are there between successive levels of the network compared to what you would expect by chance. Now, of course, again, exactly like in modularity, here it begs the question that means you already know what the levels are. You have already divided into layers, right? And so you basically do the same trick that Newman did. You said, okay, you make a guess about how many layers are there, what are the membership of the layers, then you calculate this hierarchicity index, okay? And then you make another guess, and you ask that, is this giving me a higher value of hierarchicity than the previous thing? If so, then I accept this guess and I keep improving it. Okay? So the principle is very similar, which is why I'm not going to show that slide, those slides, because it's pretty easy to understand once you get how modularity is being measured. And then I give you a few examples of hierarchic networks, like food webs is a wonderful example. So the basal species, like the plants, of course, forms the basal layer. Then the animals which feed on these plants, the herbivores, would presumably form the next layer. Then those which feed on the herbivores would form the next layer. So these are called primary consumers. Then the secondary consumers are those which feed on primary consumers and so on. So you think it's easy, right? I mean, food webs is pretty easy to work out the hierarchical layers. But there's a catch. The catch is there are also omnivores, like us, for example, who eat everything, right? We eat the basal species, we eat the primary consumers, we eat the secondary consumers, and so on, right? So this introduces links which connect, across layers. Okay, so we don't just have links between successive layers, but which also jump across layers. So this problem becomes even more complicated when you look at the brain. So, we all grew up with this very cartoon version of the nervous system, right? At one end, you have sensory neurons, which are basically directly, interacting with the sensory stimulus. At the other end, you have motor neurons, right? So, which are essentially causing our muscles to flex, okay? So, in between, you have interneurons, okay? So what the usual information flow that we think about is that information from environment causes the sensory neurons or some of the sensory neurons to fire, which then would be conveyed by layers of interneurons all the way to motor neurons, which finally will cause us to do some action. Okay? So you might say, okay, it should be fairly simple to work out the hierarchic structure of the nervous system, right? So there should be sensory neuron and maybe 3 or 4 layers of interneurons and finally the motor neuron. In reality, it turns out this is very hard to work out from any given connectome because there are lots of feedback connections. So it doesn't just go one way, it also goes the other way. Now, why would it go the other way? Anyone? Why should it go back from, let's say, motor neuron to interneurons or interneurons to sensory neurons? Sorry? Yeah. So why should feedback be there? Why is feedback important? Sorry? No, learning is mostly thought of as, like adjustment of the interaction weights. So why should you even have feedback? Yeah, so, you expect connections to mostly be directed from sensory neuron through interneurons to the motor neurons, right? Because you are responding to some sensory signals, right? But we also see lots of feedback connections. Okay, which goes from, let's say, motor neuron to interneuron, interneuron to sensory neurons, and so on. So what role are the feedback connections playing? Sorry? Adaptation, very good. Anything else? Yeah, so let's say you are looking at something, and then, you realize that, okay, something of real interest is happening on your side, okay? So you have to turn your eyes or whatever, or you have to change the acuity of your vision and so on. So all this means that you take your original information, and that original information is now processed, and then it's sent back to the sensory neurons to basically control the sensitivity or the, like you change the focus of your sensory system so that you focus your interest on where the real action is. Okay? So there's a lot of this going on even in the most primitive nervous systems. So there's a lot of back and forth connections, and of course there's also connections which jump across layers. So it's not just, you just go from sensory neuron to the first layer, then the first layer goes to the second layer, and so on. So this makes, life very difficult for those of us who are trying to understand the hierarchic structure. So for example, using this method that I've just mentioned, hierarchicity index, you will find that the human brain consists of, let's say roughly 12 hierarchic layers, okay? But if you ask what is the diameter of the connectome, okay, so anyone remember what is the diameter? Sorry? I can't hear you. The largest shortest path length, right? So you look at all the possible shortest path length between every pair of nodes and you ask which is the max, okay? So it turns out that the diameter is only about 7 or 8, okay? Now this is very confusing, right? How can you have 12 layers and have a diameter of 8? So the reason is this connections across layers, okay? It allows you to jump very quickly from one point to another point without going successively through each layer, okay? So this is what makes finding the hierarchic structure of a network, which is otherwise, intuitively obvious it should be hierarchic, very difficult, okay? So that's what the last slides of my lecture is about, which I didn't get to cover, but I'm not going to actually show it because I've got other more interesting stuff to talk about today, which is about evolution of network. And in particular, I will talk about two things, the evolution of degree distribution, in particular, how do you get scale-free distributions which have heavy-tailed, scale-free networks which have heavy-tailed degree distribution, and I will talk about something called structural balance. Okay? So, the first thing we realize is that unlike the regular or the model networks that we have seen so far, real networks tend to be highly disordered, okay, in the sense that their properties have enormous heterogeneity. So, this heterogeneity could be quantitative. So, for example, your degree could be distributed in a extremely heavy-tailed manner. So, your average degree may be 10, but you could have degree for some of the nodes as high as 1000 or even higher. Okay, so the average actually is not very meaningful. Okay, because the variance could be unbounded, for example. Or you could have extreme heterogeneity in the link weights. So, for example, look at this one. Okay, so some links are extremely strong, other links are extremely weak. So, if you look at the strength distribution of the links, that could again be a very stretched distribution. Or it could be qualitative. Okay, so the nature of interaction could be different. So, for example, some of the links could be negative, some of the links could be positive. Okay, how do you handle such, or how do you describe such networks? Okay, more to the point, in this talk, I'll be discussing how could such networks evolve in the first place. Okay, because if you were just randomly connecting nodes, you would expect what? What distribution? Degree distribution. Poisson, right? So then if you see a degree distribution which is extremely heavy-tailed, obviously there is something else going on. It's not just, links are just randomly being placed. So what kind of process can give rise to this? So these are the, interesting questions about how networks evolve. It can give us a sense of how in reality networks actually grow, okay, or how they evolve over time. Okay? Because networks are not just born, all of a sudden complete. Okay? You have creation of networks by gradual accretion of links and nodes. Okay? So what kind of process governs them? Okay. So this brings us to the second big, what do you call, event in the late 90s. So 98, we date as the birth of modern network science because of the, the paper of Watson-Strogatz essentially revolutionized the field. The very next year, Laszlo Barabashi and his then postdoc Rekha Albert wrote a paper in Science in which they focused on a completely different property than what Watson-Strogatz were looking at. So Watson-Strogatz were primarily looking at path length and clustering. So these guys looked at the distribution of the number of connections of each node. So basically the degree distribution. Okay. So what they did was they looked at 3 networks. 2 of them are in some sense social networks. So one is that same actor collaboration network that Watson-Strogatz were looking at, and the other is a co-authorship network on the Spire's archive database. So basically this is this, I think, particle physics, these are mostly, I think, particle physics papers, and links are basically between co-authors of some papers. Okay. They also looked at World Wide Web. So they asked, like, if you look at the web pages, each web page links to how many other web pages. Okay, so you look at the distribution of that quantity. All right. So what they found was that, or at least what they claimed was that in each of these cases, these distributions do not follow Poisson distribution. So for example, if you plot it on a double log scale, you will find a straight line which implies it actually follows a distribution like this. Okay. Why? Because if you take log on both sides, log of pk and log of k to the power minus alpha, you get log of pk goes as minus alpha log of k. So now if you plot log of k and log of pk on the 2 axes, then you should get a line with a slope of minus alpha. Okay. So they calculate this alpha for these various networks and concluded that each of them is actually following this with differing exponents. Okay. Yeah. So I think they just here symmetrized it. So they didn't look at the directed network in this early work. Yeah.
So in active collaborations network, for example,
Yeah.
If two people have done 5 movies together,
Hmm.
then is there one node connecting them
Yeah.
or 5 nodes?
It's just one. This is not weighted. This is not a weighted. See, remember, this is a 99 paper at which they were just interested in the degree distribution. So what you're talking about is the strength distribution. Okay.
But won't that be more reflective of what we want to measure? Like if I like 5 lines between because they have done 5 movies together versus just one?
Okay, so it turns out that the distribution can completely change depending upon whether you're looking at degree or whether you're looking at strength.
Yeah.
So degree distribution could be of one type and a strength distribution could be of quite a different type.
Yeah, that is
Okay.
why I'm asking this.
So in this particular case, they just said that, look, no matter how many movies you collaborated, it means you two know each other.
I see.
So that's the question they're asking.
Mhm.
Okay.
Okay.
Now, okay, after saying all this, let me point out that many of these conclusions have later come under question. Okay. World Wide Web and the internet are probably the only networks which still remain uncontroversial till date. That they do tend to follow a heavy tail distribution. But most social networks, when people did a much more refined analysis, they claim that they may be better fit by other heavy tail distributions such as a log normal distribution rather than the power law. So keep this caveat in mind that people are now much more skeptical about these original claims. All right. Anyway, so a little yeah. Yeah, these ones. Yeah.
So these are non-controversial.
So the co-authorship network, when people looked at the whole extent, they found that other heavy tail distributions, like in particular the log normal, can also explain it. So you can also fit a log normal distribution on this, for example.
Yeah, but at least over like 4 decades, it's power law.
Right, but the point is, if you look at a log normal distribution with the appropriate parameters, it will also show a linear regime over this range. So then it becomes a big question, which is a better thing? So then you have to ask, okay, if you look at the tail, see, in some sense, many of these papers quite conveniently cut off the tails, okay, because the tails start bending. Now that could be a finite size effect, or it could be that the log normal is actually a fantastic fit over the entire range. Okay, so because of these reasons, there's a debate raging as to how many of the networks which originally claimed to be power law are actually still power law. Okay. Yeah.
Is there any understanding as to how this log normal distribution is arising?
Yes. So log normal distribution, there's a very simple explanation for this. Okay. So why would log normal distributions arise in the first place? So I keep forgetting his name. Shockley, one of the people who won the Nobel Prize for the transistor. So they used to work in Bell Labs, right? I mean, Burdin, Breton, Shockley, all are from Bell Labs. Shockley actually has a fascinating paper on how you get log normal distributions in many for log normal nature for many distributions in reality. So the particular question he was asking is, what is the productivity of the scientists of Bell Labs? So how do you measure productivity? You can ask how many papers are they writing. Okay. So he plotted this, and the distribution fit beautifully a log normal. Okay. So then he kind of gave a very convincing argument as to why it would be log normal. So he said, look, if you have a stochastic process, but instead of being additive, as in a random walk, it's multiplicative, you would naturally expect a log normal. Why? And why is, for that matter, the number of papers should be a multiplicative stochastic process. So he says, look, The paper is the outcome of a large number of events, each of which has some probability. Okay, P1 is you have to have some idea. Okay, P2 is that idea should be actually implementable. Okay, P3 you actually get enough time to see it to fruition. Okay, but that's not the end of the story. I have got tons of results which I never had the time to write it up, right? So finally, not finally, then you have to have, you have to write it up, okay? And then, well, I'm coming to that. We are still not there yet, okay? So you write it up, but you forget to even archive it, okay? So it has to be polished and so on. So maybe it could be some kind of a draft, okay, sitting in your computer. And I have many such papers actually, which are still in draft form. I didn't even manage to get it to archive. So then you polish it up and you send it to a journal, right? And then, as Herbert says, the journal sits on it for so long, you just say to hell with it. Let me go on to the next problem, okay? So, okay, you get a review, okay? And then the review says that these authors are the biggest idiots I've ever seen. They shouldn't have even been born. This is a disgrace to the world of science. And so you get discouraged and you just file it away, okay? And that's the end of the story, okay? So with some probability, of course, you say, all right, I'm a misunderstood genius, so I'll just send it to another journal, okay? All right? So this goes on and on and on. Eventually, if all of this, things click, finally, at the end of the day, you have your paper published, right? So if each of these are independent processes, and each of them are basically numbers which are drawn from some distribution, you can think of this as basically a multiplicative stochastic process. Okay. Now, what would be the distribution that this follows? Anyone? Sorry?
You take the log and then you break it up in random.
Excellent. So you take log of this, and so what do you get? You get summation of log pi, okay? I equal to 1 to some very large capital N, right? Okay, assuming that each of these distributions have finite variance, you can apply central limit theorem, okay? So central limit theorem is a very, very useful result which says that if the first and second moment of all these individual distributions are finite, then you should actually get a normal distribution for this sum. So basically this says that this should have a normal distribution or a Gaussian distribution. Okay. Now the log of the quantity you're interested has a normal distribution. So what does the original distribution look like? So this means that whatever that original distribution is, if you took that variable and log transformed it, then that distribution would look like a normal distribution. Yeah.
The probability pi
Yeah.
is itself a distribution. Then the probability,
No,
probability.
PIs are numbers which are drawn from distributions. Okay, so each of them could come from some different distribution. Okay, so this could come from some distribution capital P1. This could come from some distribution capital P2. This could come from some distribution P3. The only thing that is common across all of them is that they have finite first and second moments. That's when central limit theorem applies. Okay. So log P has a normal distribution. So the question is, what is the distribution of P? Okay. So it turns out that if you have log x going as a normal distribution, x would have a distribution which looks like this. Okay, and this is the log normal distribution. In other words, it means that if you did a log transformation of the variable, then the log transform variable would show a normal distribution. All right? So, in some sense, if you have no better knowledge of the system, the null model of a log normal distribution would be a pretty good guess. All right? Okay, so I had mentioned Mark Newman's paper, Power Laws, Pareto Distribution, and Zipf's Law during the first tutorial, right? When I was talking about, how do you actually calculate the cumulative distribution by, the most efficient or economic use of your data points. So this is the paper. So it appeared in Contemporary Physics in 2005. So it's an excellent paper where he makes it very, very clear, how do you actually measure power laws in a robust manner and so on. So this is basically just a retelling of what I just told you, that why is it that when you plot a power law in a double log scale, it should appear as a straight line with a slope minus alpha. And the reason why it's sometimes known as scale free is that if you compare it with other distributions like the exponential distributions, these distributions have a characteristic scale. So for example, exponential distribution would have this form where you will have something like e to the power minus the variable divided by some characteristic value of that variable. So this could be either a time or a length or whatever, and the mean and the standard deviation both for exponential distribution happen to be the same. And so one of the wonderful examples of such exponential distribution is the half-life distribution. So here tau is basically the characteristic time. Okay, or if you are interested in less esoteric things, you could be looking at the waiting time between buses to arrive. So if there is no correlation between them, then you would expect that the waiting time between successive buses arriving at a bus stop would have an exponential distribution. So typically whenever the events are independent and occur at a constant average rate, so these are what are known as points of processes, you would expect an exponential distribution. So the important thing to note is that these are always having a characteristic value. By contrast, there is no characteristic value associated with this distribution. This is just an exponent. Okay, so in other words, it doesn't have any microscopic details of the system in the distribution. Okay, so whenever you see a power law, that's why people kind of suspect universality of some kind. That's because there is no microscopic details that need to be invoked of the system in order to explain that distribution. So physicists get so obsessed with power laws is because they say that, okay, maybe I don't need to know everything about this underlying process going on in the system to explain how this distribution can come about. Maybe there is some kind of a universality. Okay? So the other interesting property for power law distribution is that compared to the usual distributions we are familiar with, like the normal distribution or the exponential distribution or the Poinsot distribution, these tend to have very, very long stretched tails. So we often call them heavy tail distribution. So in the context of a network, what this means is that if you are looking at a degree distribution which is a power law, that means that even though the average degree could be very small, like 10 or 5 or whatever, there would be significant probability of having nodes which have extremely large number of links. So these nodes are given a special name. They are called hubs. So hubs, as the name makes it clear, has this analogy with the hub of a wheel. So so when you look at a wheel, you have this central point from which these spokes radiate, right? So the hubs of a network has that kind of visual impact. So they basically have, so most of the nodes have fairly few links, but there is this node over here which has all the links radiating out of it. So that's why they are referred to as hubs. So the existence of hubs is very characteristic of networks having a power law degree distribution, which has an extremely stretched probability distribution tail, which essentially means that compared to a normal distribution, the probability of having a node with a high degree is very high. Right? So that's where the scale freeness comes from. So the question is, how do you get these kinds of networks? So if you are not bothered about trying to invoke a particular process, you just say, I want a scale free degree distribution. I don't care how I get it. Okay, I want to create a random scale free distribution for my study. So there's a very nice generalization of the Erdős-Rényi random network model by which you can get random networks with arbitrary degree distribution. Okay? So the Erdős-Rényi of course gives you a Poincare distribution, but suppose you say that, look, I want to generate a network with any distribution I want. Okay? How do I do it? Okay? So usually then people use what is known as the configuration model. Okay? So the configuration model differs from the Erdős-Rényi random network model in the sense that now instead of just a Poincare degree distribution, you can actually have any desired degree distribution that you like. So how do you do that? Well, first you look at what distribution you want. Let's say you want a scale free distribution, or you want a log normal distribution and so on. So you specify the distribution with the parameters, and then you start drawing integer values from that distribution. Okay? So let's say you want L links, so you draw L numbers from that distribution. So by definition, those L numbers, each of which are basically, sorry, what am I saying L numbers? N numbers, because these stand for degrees. Okay? So you draw N numbers from that distribution. So by definition, since you're drawing it from a specific degree distribution, that means those numbers would be following, it's a sample from a particular distribution, right? So those numbers has to follow that distribution. Right? No, the degree, because it's a degree distribution which you want to follow a specific distribution, right? So you're drawing the degrees. So basically you're asking that I have n nodes, what would be the degree of these n nodes? So you draw n numbers, okay? So essentially then now by design you have a specified degree distribution. Now the question is, how will you actually make sure that the network has that particular degree, right? So what you do is you take the first number, okay, and you put stubs on, oh sorry, let me just wipe this. So take your first node, and let's say you drew the number k1. Okay, so what you do is you put such stubs coming out of it, k1 stubs. Okay, then you draw the second number, k2. You put those stubs, k3. You put those stubs and so on. Okay? So after many of these things, you finally get. So now you have basically put in the stubs. Okay? Now what you do is you start picking up pair of stubs in two nodes and then matching them. Okay. So you randomly draw two numbers, I and j, and you ask, do each of them have free stubs? Okay. If they have a free stub, you start linking them. Okay. So you carry on this process until there are no free stubs left. Okay. And then you will get a network which has this specified degree distribution. Yeah. Sorry? Okay, so if you are doing independent drawing, so sometimes this will mean that this will give rise to either a self-link. In fact, if you deliberately avoid self-links, you are going to soon arrive at a situation where you are extremely constrained, because there's, let's say you match everything and finally you are left with a node which has 2 stubs coming out of it, right? So then you'll have to connect it. So you will have certain self-links. You'll also have some situations where you'll have multiple links. Okay, so I and j could be connected by more than one link. Okay, but one can show that as n tends to infinity, okay, this probability will actually go to 0. Okay, so that's why this can be shown mathematically actually. Yeah. Right. Okay. So that's how this works. Okay. So you would say that okay, that gives me a nice procedure for generating random networks with arbitrary degree distribution. I don't need to just have Poisson degree distribution random networks. Okay. But this leaves the question open. Yeah.
Sorry, about the question you were asking.
Yeah.
Is it because of equivalence of ensemble in a sense that if you had a fixed number of edges,
Yeah.
instead if you had a distribution of the nodes, degree of the nodes, I mean, is there like these two ensembles are equivalent? Is it?
I didn't understand. Can you say that again?
In the previous sense you said there is a L edges.
Yeah.
And probability of each node being connected to another node is P. So there was there was 2 ensembles and one ensemble was easier to work with.
Ah, okay, they're very nice. Actually, I forgot to mention. So this is actually analogous to the GNL random graph model.
But
Okay.
you said in the larger limit you can always get a true network. Is it
Yeah.
because of
Actually, I haven't thought of it that way, but you might have a point. Okay, I never thought of it that way. But yeah, if you look at the proof, maybe what you are saying is what actually is happening. Nice point, actually. Okay, yeah. So you can get a network with whatever distribution you want, and so therefore you can also generate a network with a scale-free degree distribution. But that leaves open the question: why in nature or in reality will we get scale-free degree distribution in the first place? So there should be some mechanism which generates a degree distribution which has the scale-free nature, right? So Barabashi and Albert proposed a mechanism by which this can actually happen. Okay, spoiler alert, it turned out that unknown to them, somebody else had proposed exactly the same mechanism decades earlier. Okay, as in science, as happens many times in science, if you think you have a great idea, chances are that somebody 30 years back also had that same great idea. Okay, so but anyway, I'll come to that later. So they proposed, so that's why I call it the Price-Barabashi-Albert scheme, because it was Solar Price who actually first proposed this. Okay, so nowadays it's also called Price-Barabashi-Albert rather than just Barabashi-Albert, to credit Price who actually first thought of this. Okay, so they said that, look, one way in which we could get this kind of scale-free degree distribution is the following, that you don't have a network of n nodes right at the beginning. You start with, let's say 1 or maybe 2 nodes, and then keep adding nodes at successive time points. Okay? Each of these nodes comes with some fixed number of connections. Okay? So let's say that every node that you add has m links associated with it. Okay? So now you have to connect this m links to the existing number of nodes that are already there in the network. Okay? How would you connect them? Now, if you say that these nodes are going to be connected completely at random, then no surprises that you will get something which is almost equivalent to an Erdos-Renyi graph. That is, you will get a Poisson degree distribution. But suppose it's not occurring at random. Suppose the new links, the new nodes which are coming in are preferentially connecting to nodes which already have lots of links. Okay? Now, you might say, why? Okay, think of social networks. If you have a group where there is, some very popular guy, then the new people who gravitate to the group would first, fall in line with this popular guy. Okay, you are much more likely to, because the popular guy obviously has some characteristic which makes him or her very likely to they're like very extroverted. So they kind of they see someone out there and say, hey, my name is this. What's yours? What are your hobbies? Where do you hang out and so on. So you're very likely to connect to someone who is already having a lot of links. Okay. So in a sense, you might say that the probability that this new node which is coming in would connect to an existing node is proportional to the degree of the existing node. If this existing node has k connections already, then the probability that one of the links of this new node will connect to that is actually going to be proportional to k. So this is called the linear preferential attachment. You can also say that it could be proportional to square root of k, k square and so on. It turns out that it somehow sensitively depends on this linear scheme. So if it is k square or k cube, you actually don't get a scale free thing, but you get something else. Okay. Anyway, so suppose you say that you have a probability of this new node connecting to a node of degree ki with this kind of probability, ki by summation over all the k's. Okay. Then so basically how does this network evolve? So initially you have this two nodes which are connected by a link, and then a new node comes in. So in each of these figures, the nodes which were there in the previous panel are colored black, and the new node is colored white. Okay, so you can see these two nodes were already there. Then the third node comes in. Each node comes with two connections, right? So here, since there are only two nodes, there is no choice. You connect to this node and you connect to this node. Then the fourth node comes in. Now the fourth node has to make a choice, right? Because it has two connections, but there are three nodes. So let's say, because each of these nodes have exactly degree 2, it just, tosses a coin and decides, okay, I will connect with this one and this one. Now the moment this choice is done, you've broken a symmetry, right? So now these two nodes each have degree 3, and these two nodes have degree 2. So then when the next fifth node comes in, then it will, with a slightly higher probability, connect to a node with degree 3, and then because there's always a probability that it will connect to degree 2, let's say it connects to this one. Then this one now has a degree of 4, this one has a degree of 3, and this has a degree of 3, this is a degree of 2, and this is a degree of 2. So then when the next node comes in, it would basically preferentially connect to this node which has already degree 1, 2, 3, 4. So now it connects to this. So now you see what's happening. As time goes on, the node which somehow accidentally happened to attract a few more connections initially will become more and more likely to connect to. Okay. So it has this advantage which occurred simply by chance initially, which it builds upon. Okay. So as a result of this, very soon these nodes which early on attracted a few more links by chance would tend to become hubs. Okay. And so you'll have structure which looks like this. And you can show that the degree distribution would actually tend to follow an exact power law with an exponent of 3. So basically the P of k would go as k to the power minus 3. And you can show actually this analytically. Okay. Now, the spoiler. It turned out that this process was published way before Barabash and Albert published their paper. In fact, all the way back to 1976. Yeah. Is the exponent tunable? Can I modify it? Yeah, short answer, very difficult. Okay. So it turns out that this linear preferential attachment scheme is very special. You try to make it k to the power 2, k to the power 3 or root k, everything breaks down. It doesn't even follow a scale free nature. So the only way to get different exponents is to add other features, like for example, you say that nodes have different intrinsic attributes. Some are more important than others and so on. But it makes the model much more ugly, right? Because you're assuming lots of things. Okay. So, like as I think Pauli once said, right? that the more parameters you have in the system, the more things you can do. So what's the surprise? You know, he said if I have 3 parameters, I can fit an elephant. If I have 4 parameters, I can make the elephant wag its tail. So that's the problem with this, models which built upon the preferential attachment scheme. You can force the model to have other exponents, but then you lose the simple elegance of the original model. Okay.
Sort of too good to be true. Like you put in a simple rule and you get a power law.
You might say that. Okay. So, so this person, Derek Sola Price, okay, again, I always get distracted in my talks because, each of these people has fantastic, what you call backstories behind them. Okay. Whenever, you see a scientist who has contributed something interesting, it turns out that's just the tip of the iceberg. This guy has also done other very interesting things which we don't get to know because he's just too famous for that one thing he's done. So Sola Price is known to network scientists because he was the first person to have proposed the preferential attachment scheme. But if you ask bibliometrists, so once I was talking to this guy from the Thomson, who actually runs this citation index services, ISI or Thomson Reuters or something. So their salesperson once came to our institute to try to sell us the license to look at this. Yeah, exactly, Thomson Wave of Science. Okay, so it turned out that so we were just talking, and then I was telling him about Sola Price, and then he said, "Is this the same guy who came up with citation thing?" I said, "I didn't know that." So it turned out that bibliometrists, so people who work on scientometrics, know Sola Price for having come up with this idea of this. How do you count impact factor? Okay, a citation. So it was Sola Price who came up with this whole idea. And the reason why Sola Price actually came up with this idea is also very interesting. So he used to teach at Raffles College in Singapore, which is I think now the National University of Singapore. Okay, so he was a physicist by training, by the way. So all good things that have ever been done in science are actually done by physicists. I like to claim that. Okay, so he was teaching physics there, and then Raffles College decided to demolish the library and rebuild it. So then the question was, what do we do with those volumes? Okay, so they didn't have enough space to put all those volumes in their storehouses. So they did the next best thing. They said, all faculty members, please volunteer to take so many books and journal back issues to your house and store them, okay, until the building is rebuilt. So he volunteered to take the entire set of back issues of Proceedings of Royal Society dating from 17th century. Okay. So he had this brand new apartment then, which had all these empty shelves, which he still hadn't time to fill. So he decided to, he had plenty of time in his hand in some extended weekend. So he decided to do this. He said, okay, each shelf I will house 1 decade worth of Proceedings of Royal Society. So he starts by, putting, let's say, the first decade, okay, this many volumes. Second decade, this many volumes. Third decade, this many volumes, and so on. So he does this arrangement, steps back, and says, wow, that's a smooth curve, and that's an exponential growth curve. Okay, so if you think of the total number of pages of the journal as somehow measuring how much science is being done, you see that there's been an exponential growth of science. Okay, so after that he started, of course, quantifying this in a great detail, and that's when he shifted from physics to scientometrics, basically asking, can you measure the progress of science? So he came up with this idea that actually science grows in an exponential manner, and so unless you can build some technological fix by which you can access this enormously expanding body of knowledge, very soon it goes out of hand. Okay. So how do you then find the important stuff from the dross? So is there some way you can measure important papers from the rest. More to the point, suppose you're a librarian, the number of journals are exploding, right? So, you have only finite budgets. So you have to make a decision, which journals do I keep, which journals do I don't keep, okay? Now, in many institutions, like for example, in Indian Statistical Institute, when I was doing my PhD there, the library had only a very few physics journals, which it used to keep. And much to my surprise, I found that they don't keep physical review letters, they don't keep any of the physical reviews, but they keep Nuevo Cimento. Okay? So this was a big surprise to me until I realized, well, there's politics involved, right? So there's a whole group out there who were, publishing tons of papers in Nuevo Cimento, and according to them, Nuevo Cimento is the best journal in physics. Now, what is PRL? I mean, so, Nuevo Cimento is there, but PRL is not there. Okay, but politics aside, suppose you're a librarian and you really want to make a, unbiased judgment as to which journals to keep. How do you do that? Okay, so you ask, okay, which journal is publishing the most important papers? And the question is, how do you realize, how do you guess most important papers? You don't have the time to read through all the papers. Okay, it's impossible. So then you ask, okay, if it's important if other scientists are reading them, and how do you know other scientists are reading them? If they're referring to them. Okay. So then he said, okay, so I will look at the bibliography of the papers which are coming afterwards and see how many of the papers of this journal is being cited by these other papers. And so that's how this idea of impact factor was born. Okay. So impact factor today is of course abused enormously. It's used to measure the productivity of individual scientists, but Derek Solar Prize was very clear. It's not meant to measure the contribution of individual scientists. It's just to help librarians decide that if you have a finite budget, which journals I should keep. Okay, so you can rank the journals by, in some sense, their importance, and then you can decide, okay, maybe I will choose to, keep this top journals in terms of the impact factor, because these papers seem to be read by more scientists than other scientists. So it's a very democratic way of, figuring out which journals to keep. It was not meant for anything else. Okay, end of diversion. Okay, we come to this one. So this is related, of course, related to his other career of scientometrics. So you can see that this paper was published in a journal which physicists normally don't read. Journal of American Society for Information Science. So no wonder that no physicist ever heard of it. Okay, but what was he saying? So he was asking that you often see that a certain paper is a citation classic. So he was basically questioning himself. So he was saying that you have papers which have received thousands, 5,000, 10,000 citations. But does that automatically mean that a paper which has received 5,000 citations is 5 times more important than a paper which has received, let's say, 1,000 citations? Or a paper which has received 500 citations is more important than a paper which is 5 times more important than paper which has received 100 citations? Is there an actual qualitative correlate to the number of citations that a paper receives to the value of the science which is being reported? Or could there be sociological issues? Okay. So in this paper he suggested that, look folks, the reason why papers become citation classic could have more to do with the way humans behave rather than the quality of the science that is reported. Okay. So he came up with this idea that, look, often what happens is you are writing a scientific paper. Okay. So you have written everything, the important stuff where you have reported what your work is and so on, but you have to write the introduction. Okay, so in the introduction, typically you write a background, and when you're a student, it's actually the least important thing, right? When you're an advisor, it's exactly the opposite. Okay, the introduction is the most important thing because you got to motivate. Okay? Otherwise, the editor will just junk the paper, won't even go into what you've done. Okay, so your advisor says, where's the introduction? You have to give a good, background and how your paper fits into the history and so on. And I think this is a waste of my time. So what do? You say, okay, which are the 2 papers I read while, trying to write this? Let's look at what papers they have cited in their introduction. So So you don't even bother to read up those papers, you just copy those references. Okay? So now your paper gets published, and the next student who comes into your lab says, oh, my senior wrote this paper, maybe I can just, paraphrase his introduction. So let me just copy those papers also. So you can see what is happening, right? Initially, just by accident, let's say somebody chose to cite some papers, and then others are just copying those citations, and those papers are now receiving huge number of citations simply because they've already appeared in 100 papers. So, you're much more likely to be visible. Your paper is much more likely to be visible than another paper which has probably been cited in only 10 papers, right? So you accumulate this advantage, and eventually you become invincible. Once you have appeared in 1,000 papers, you are going to, just keep growing, okay? So the more wealth, in the sense of citations you have, the more rich you will get, okay? So this is a, sociological process. And by the way, there have been very interesting studies done on how, so you might say, how do I know that, people are actually copying this, okay? So there is a very interesting paper which actually looks at how, when you copied some paper's information, let's say you made a mistake. Let's say you quoted the wrong volume number or the wrong page number, okay? So the next person who comes and copies you actually copies the mistake also, right? So it's a bit like mutation, okay? So there's a mutation, and then, the mutation gets carried on. So by, just as through mutations you can build phylogenetic trees of organisms, you can build phylogenetic trees of citation networks. So there's this paper which actually follows, how these errors propagate. So you can see that, some guy made a mistake in the last digit of a page number. Let's say it was originally 571, and he wrote 577 because 1 looks very similar to 7 when you handwrite it, right? And then at some point it becomes 517, okay? And then it keeps getting carried on, and then somebody writes 617, and so on. So it gets more and more mutated. So you can actually follow how such errors in copying are actually going through, and thereby you can almost prove that people actually don't read those papers. They're just citing them, okay? And of course, once one biologist told me, again a biologist joke, okay? Once some biologist told me, look, biologists are happiest if no one reads their paper but just cites them. Because once you start reading them, you realize that there's a lot of ghapla going in. Right? Okay, sorry about this bio jokes. I mean, these are things I just do to rile my wife. So, yeah, so this is also sometimes known as Matthew effect. So this comes from the very famous phrase in Bible, which says, for to all those who have more will be given, and they will have an abundance, but from those who have nothing, even what they have will be taken away. So this, was actually pointed out by, I think, Robert Merton was probably an economist. I don't remember what, he's a sociologist. So he had actually written a beautiful paper where he said that if you write a paper with a well-known scientist, you might have done the donkey work, but the credit all goes to the well-known scientist. The well-known scientist might have just, actually might probably have not even looked at your paper, just lent his or her name. But everybody will know this as that famous scientist paper, and you are forgotten, okay? So it's a sad, sorry.
Might add to the story. Somebody introduced himself, I am et al.
Extremely great story. So in fact, there was actually a paper in Nature where there was a single author, I think, I'm forgetting the name of this guy. So one of my former friends said that, oh, have you seen my paper in Nature? So I went and looked up the paper, and I see this single name which is not his name. So I emailed him, what your paper? Your name is not even there. He said, look at that asterisk. And so there was this small asterisk after the name, and the asterisk says, look at supplementary material. And the supplementary material has this entire list of authors. Yeah, so So why is the distribution scale free? Okay. So yeah, so this is 1230. So I would have loved to go through this derivation, but this will take some time. So what I will do, if you permit me, is I'm going to actually skip it because it's fairly self-explanatory. So basically you start with, evolution equation of the degree of the ith node. So you can see that, here you assume that every node comes in with m links, and then there's this m times the probability that you are going to attach to the ith node with degree ki. So, this is this expression of this linear preferential attachment probability that I already mentioned. So you write down this equation, then you essentially solve it, and if you follow through all of this, you will show that this results in a cumulative degree distribution, which you then convert to the probability distribution of the degree, which apart from a factor which is related to m, would give you a k to the power minus gamma factor. Now this k to the power minus gamma factor actually turns out to be nothing but 3. Okay, so you can actually analytically show that why the linear preferential attachment scheme would give you a degree distribution of p of k going as 1 by k cube. Okay, but I'll skip it because I have some more interesting stuff left to say. So after they published this paper, people asked, okay, so what? So you have a scale-free network. What is so special about it? So in subsequent papers, Barabashi's group actually went on to show why scale-free network can have actually properties pretty different from other kinds of networks. In particular, they showed that the fact that there are special nodes, hubs, which have lots and lots of connections, but which are actually very, very rare, makes the system behave very differently from homogeneous network when it comes to things like failure. Okay, so people have related this to, for example, percolation. So if you start removing nodes at random, you ask when does the network break down. Okay, so in a similar spirit, you can ask that suppose I'm randomly removing nodes in the system. Okay, so at what point does the connectivity of the system break down? Does it get fragmented into distinct clusters? So it turns out that for scale-free networks, you can delete an enormous number or enormous fraction of your nodes and still the network will remain connected, because the probability that you are going to be hitting all the nodes initially would be very low, because let's say out of a million nodes in the network, maybe 10 are hubs, but those hubs are very important in connecting the system. So if you are just drawing nodes to be deleted with equal probability, it's very, very unlikely that you'll be hitting all 10 nodes before you remove a huge number of nodes already. Okay, so the network will remain connected even if you have, for example, removed, let's say, 99% of the nodes. Okay, so hubs play a very, very important role in maintaining the, I saw your question, I'll just come back in a moment, in maintaining the integrity of the network. But at the same time, so this is like, if you are looking at the internet and you're looking at random breakdown of, servers and so on. But suppose you are a terrorist, okay, and you want to bring down the internet, okay. So of course you can do a denial of service attack by, trying to attack millions of servers at the same time. But you can have a much more smarter thing. If you already know which are the hubs, you will just target the hubs. If you bring down the hubs, so this is called, selective attack or degree-based, breakdown of nodes. So if you do a selective attack, then just by attacking 10 nodes, you would have severely damaged the network, because the rest of the other nodes actually play a very minor role in keeping the network connected. So now, once you have taken out 10 out of those million nodes from the network is going to start processing information at snail's speed. Okay? So this is known as the Achilles heel of the scale-free network. At one hand, it is extremely robust to random breakdown, but at the same time, it's highly susceptible to targeted attack. Yeah, sorry, what's your question?
No, just wanted to make a comment, like this can be, I think, used to my previous discussion, like how can we quantify defects in an network?
Well, it's not so much defects because you are asking which are the most important nodes in the network.
Exactly. I mean, even though there are neurodegenerative processes happening throughout our age, I mean, as we age, what happens is that there are like certain parts of the brain that still keep up and make us functioning as throughout our life progresses. So, yeah, that's what I was thinking.
Yeah. So the only problem is, of course, brain networks are not scale-free. Okay. So you don't have this kind of a very lopsided distribution where one brain region has, several orders of magnitude more connection than other regions. But your question is still important because degree is only one way we measure the centrality of a node. Remember I started my talk with eigenvector centrality, which is a very different concept of centrality. So I mentioned, right, that if you want to know which is the most important node in the network, you can look at the number of connections. But then it's easy to fool that system because you just ask a lot of friends that, I will give you a link, you will give me a link, okay? Instead of that, if you now look at eigenvector centrality, okay, that's an even more robust measure of importance, okay? So you can look at eigenvector centrality, for example, if the network is not scale-free, but there are other ways also. So for example, something which I didn't get to yesterday was if you look at a network which is modular, as typically brain networks are, you can start asking the question, which nodes play the key role of connecting otherwise isolated modules? Okay? So if something happens to them, coordination is broken between these various modules. So they are not nodes in the sense that they may not have many connections. Sorry, they are not hubs in the sense that they have too many connections, but the connections they have are very important because if you take them out, you basically make them fragmented. Very similar to what is happening here. So it depends upon, whether your network is scale-free or not. So if your network is not scale-free, you can still talk about importance, but you have to talk in terms of importance using other measures. Okay, so how does it affect other things? Like for example, epidemic propagation, because this is something that, I'd been talking occasionally. So in epidemic propagation, one of the most common models is this, and I think yesterday someone asked me about, how do I model epidemics on this modular network? So typically people use this so-called susceptible infected recovered model, which was proposed back in the 1920s by these people, Kermack and McKendrick, who it turns out are not even mathematicians. So McKendrick was a doctor and Kermack was a chemist. So what were they doing, devising all these equations? So it turns out McKendrick was a protege of Ronald Ross, and Ronald Ross had this bee in his bonnet that we need to eliminate malaria, and he had some thoughts about how to eliminate malaria. Namely, he said that basically we get rid of all the breeding grounds of the carrier, the vector, that is the mosquito. Now the usual retort to Ronald Ross's proselytizing zeal from the administrators. So he went to Sierra Leone, which was then a British colony, and he said that to the British administration that you have to hire people who are going to make sure that there are now puddles where rainwater can accumulate, and then you'll get rid of malaria. So malaria was a huge problem in Sierra Leone. I mean, the life expectancy of the typical European soldier was something like a few months. Okay. So initially they tried it out. So Ross thought that if he actually showed this in Freetown in Sierra Leone, then people will be convinced that he's right, and then this would be adapted throughout the British Empire. The problem was this: they did it for a few months, and then the typical bureaucratic response: it's costing too much money, but is it really having an effect? And so the bureaucrat said that, and then one bureaucrat made this fantastic point. He said, mosquitoes are God's creatures too. God has put them on this earth for a particular reason. Who are we to eliminate them? Okay, impeccable argument. And some other bureaucrats said, it's impossible to eliminate one species. We can't eliminate all mosquitoes. Why? So, why waste money in trying something which is impossible? And that was the end of that experiment. So then Ross realized that, you can't actually do control experiments because bureaucrats are just too stupid. So can we do this? Can we show this mathematically? And so that's how the first epidemiological model happened. So the first person to do epidemiological modeling, it turns out, is not a mathematician, but a doctor, Ronald Ross. So he did a very nice model of how malaria spreads. And then McKendrick was one of his proteges, also a doctor. And McKendrick was basically thinking that, Ross has done this model for malaria, but can we do a general model which applies to all epidemics? So since he himself was not a mathematician or trained in mathematics, he wanted to find someone who could do the maths for him. And Kermack, who was by training a chemist, happened to be the right person because through a tragic accident in the lab, so like chemists at that time used to do some pretty dangerous stuff. So he happened to do an experiment which literally blew up in his face, and he lost his eyesight. Okay, so in the hospital, he kind of, basically had people read maths books to him, and that's how he learned calculus, okay, differential equations and so on. And he was, he wanted to work on some problem. He can't work on the lab, but he can do mathematics. So somehow Kermack and McKendrick came together, and McKendrick told Kermack, can you do something about it? And out comes this brilliant set of very simple equations which are still used today. Okay? So the equations are pretty simple. So it basically has three variables: the number of susceptible individuals, the number of infected individuals, and the number of recovered individuals. So how does these numbers change? So beta is the rate at which an infection spreads. So if you have an infected person meeting a susceptible person, then with the rate beta, the infected person passes this pathogen to the susceptible person, and so that person becomes infected and then goes on to augment the infected population. So you can see that the same thing, beta Si, appears with a plus beta Si. So the loss of susceptible is the gain of infected. All right? Now you'd ask, why is this a product, S into I? Okay, so that's because the model assumes homogeneous mixing. It says that any person in this population is equally likely to meet with any other person. So what's the probability that a new infection will happen? It's proportional to the probability that an infected person meets a susceptible person. So what is that probability? If you assume that everybody is equally likely to meet everyone else, it's just proportional to the population of susceptible individuals and the population of infected individuals, right? It's like Ki into Kj kind of thing, right? And beta basically tells you out of how many such interactions between susceptible and infected individuals, how many of them would lead to actually a new infection, all right? So this is the reason for this, and then you have a minus I by tau. So what this is telling you is, so 1 by tau or gamma is the rate at which infected individuals are recovering. So this could be either, they are actually recovering, or they could be removed by death also. Okay, so fortunately R can mean both recovered and removed. Okay, so you don't have to distinguish between whether they are dying of the disease or they're just recovering. In any case, whether they are dying or whether they are recovering, once they have recovered, they are no longer contributing to the infection. Okay, so over time you can see, so this is, the red curve is the number of infected people over these many days. This is the number of susceptible individual, and this is the number of infected individual. So what you are doing is you are changing the contact rate. So as you change the contact rate, you can see that how fast the epidemic actually occurs would start changing. All right? So the important part is, if you do these calculations, you find out that whether an epidemic occurs or not depends on the product of three quantities: N, which is the population size; beta, which is the rate at which the infection spreads; and tau, which is the period for which an infected person remains infectious. So this product also goes by a very special name. It's called the basic reproduction number, or R naught, something which we have got very familiar with during the COVID epidemic, because even journalists who don't know any maths would be actually talking about basic production number, or R naught. Okay? Yeah.
You said that the recovered are the one that either died or got uninfected. So they will not contribute to the infection. So during COVID, like the infected people can, like the person who has actually recovered, they can get reinfected. So how can we deal that thing over there?
Very nice question. So in fact, that is precisely the model I was showing yesterday. So that is a generalization of the SIR model. It's called the SIRS model. So there you have got another term here, which basically says that with some rate alpha, so minus alpha R. So with some rate alpha, recovered people are becoming susceptible, and you would have a term plus alpha term here. Okay? So if you just make that small change, then you can model this situation where with some rate alpha, people who have recovered again become susceptible because they lose the immune defense. Okay? So it turns out that before COVID, SIRS models were not so popular because there are not that many diseases which don't give you lifelong immunity. So most diseases actually give you lifelong immunity. Okay? The few exceptions were syphilis and some other diseases, for example. So because of that, because people said that this is not not too many diseases have this. SIRS models were not very popularly studied, but suddenly COVID came and SIRS model became extremely popular. Okay. But so using Kermack-McKendrick, you can do a whole. I mean, this is just the basic model. You can also do SCIR model, so susceptible, exposed, infected, recovered. So you might be exposed to the disease, but you are not yet infectious. Okay, it's incubating within you. Okay, so after some time you will basically get infected. So SCIR models are very important, for example, when you're studying HIV, because you could have incubation periods as long as 10 years. Okay, so if you try to model HIV progression with SIR model, you'll fail badly. So you need to bring in the fact that they've got enormous incubation periods. Okay. Anyway, so if you use this set of equations, it turns out that you can actually calculate what is the critical number of people you need to immunize in order to stop the epidemic. Okay? So what do I mean by stopping the epidemic? It means that what do I need to change such that DIDT becomes negative? Okay? Because DIDT is basically telling us what is the rate at which number of infected is growing. So epidemic is defined by being DIDT being positive. So if DIDT is negative, that means even the initially infected population is gradually decreasing with time. So you want to know under what conditions would this become negative. So what you say, okay, that simply means that beta Si has to be less than I by tau, right? So because in the initial stage of the disease, the number of the susceptible population is almost equal to the total population, you can replace this S by N. Okay, so then you get the condition beta Ni is less than I by tau, right? So I cuts out from both sides. So what do you get? N beta tau has to be less than 1. Okay, so in other words, this number has to be less than 1. So that's why this is actually so important. Okay, now that's the condition of epidemic. So now when you start vaccinating people, what is happening? You are reducing the initially susceptible population from N, right? So suppose you have vaccinated N prime people, okay? So what's the susceptible population now? It's N minus N prime, right? So now you are basically calculating the quantity N minus N prime beta into tau. So if N beta tau was greater than 1, if N prime is sufficiently large, then N minus N prime times beta times tau can actually be less than 1, right? So you ask, what is this N prime, or typically what is the ratio of N prime to N, which I need in order to turn this from a greater than 1 to a less than 1, okay? So it turns out very conveniently that this is nothing but 1 minus 1 by this R naught, okay? So if you know R naught, so which you can, estimate from the, how the number of cases are growing, you can actually work out what is the critical number of the critical fraction of the population that you need to vaccinate in order to stop the epidemic in its tracks. So if R naught is 2, for example, then you need to vaccinate at least 50%. If you have R naught equal to 3, you need to vaccinate at least 66%. Okay, this is assuming 100% effectiveness of the vaccine. If the vaccine effectiveness is, let's say Q, then obviously proportionately this number will start increasing. Okay, so you can show that if the vaccine effectiveness is, something like less than 60%, it's actually pointless, because you need to vaccinate 100% of the population in order to have any effect, right? So that's why people are so interested in first measuring the vaccine effectiveness. If it is less than some critical fraction, they don't even bother with rolling out the vaccine. Okay, but the important thing is this critical threshold that we are talking about goes for a toss once the contact network becomes scale free. Okay, so in this brilliant paper, Berguina, Pastos-Satoris, and Vespinani showed that if you have a scale-free network, then actually the condition is not n beta tau greater than 1, it's actually n beta tau average degree by the second order moment. And if it's a scale-free network, we know that if the exponent is less than 3, this actually goes to, this diverges. So if you divide something finite by something which is diverging, you get 0. So in other words, you are going to have an epidemic no matter how many people you are vaccinating. So in practice, what is happening? In practice, what is happening is that if you are randomly vaccinating people, then the probability that you are going to also be able to vaccinate all the hubs together is very low. Okay, so even if one hub is left behind, that hub, once it's infected, would be able to infect a significant fraction of the network. So what was, in some sense, the ability of the scale-free network to resist, node removal at random also makes it extremely evil for contagion propagation. Okay? Now, after they published this paper, there was a panic attack in, many communities that, that this means that vaccination is useless and so on. So then Robert May, another physicist turned epidemiologist, ecologist, came up with a very nice paper where he said, hold on folks, before you start panicking, let's ask ourselves, are real social networks along which infection spreads scale-free? And he showed that, look, for most diseases, it's not scale-free. Real social networks are not scale-free. They're mostly following exponential distribution. So we don't need to start panicking. However, there are exceptions where it may be true that the effective network is actually scale-free. And one of these cases is the network along which HIV spreads. So remember I said that incubation period in HIV, or the period in which, or even the period in which you're infectious but you're not showing any of the symptoms, could be very long. So you are not knowing it, you are spreading the infection along. By the time you start showing the symptoms, it's already late. You've already infected hundreds of other people if you're sexually promiscuous, right? So if you look at a sexual contact network with diseases which have long periods in which it's latent inside you, so you're infectious but you're not showing any symptoms, then actually your social network is not an instantaneous snapshot. So in COVID and so on, it's an instantaneous snapshot. You are only infectious for a few days. Okay, so you just look at right now what is your social network. But for something like HIV, you need to look at how many people you came in contact with, let's say over 10 years. Okay, and over 10 years, you might have come across many individuals. Okay, so you're actually accumulating all these contacts, right? And so this, it turns out, could be scale-free under certain conditions. In fact, there's this famous case of patient 0 in HIV, right? Supposed to be some steward of some airline who actually brought the disease to North America and started spreading it around. Okay, so in such networks, it's possible that scale-free nature of the network could be responsible for spreading the disease. Okay? But for most diseases, we don't need to panic. it is not going to be like that. Okay. Okay, I'm almost out of time, but anyway, so the question is, are real networks really scale free? So as I mentioned, most reports of scale free networks after Barabasi and Albert's paper were like this. Okay. If you take out this guiding line, okay, Bob's your uncle. What is this curve? Is this curve like this or this? You know, it's like on a hope and a prayer. You're saying that it's a power law, right? So most reports were like this, and there's this nice paper which came out in 2006 by Khanin and Witt, who did a very critical analysis of the data sets that were claimed to be scale free and showed that there is very little evidence for scale freeness. Okay. In fact, just before COVID, another very interesting paper came out. I think by Closet and co-workers, which actually did a rigorous reanalysis of many of these earlier data sets and showed that there is no evidence to back up the contention that these networks are scale free. Okay. So right now I think only very few networks actually are there for which the scale free nature is actually completely uncontroversial. Okay. Also, you might start asking the question that, are there other ways of getting scale free? So there's this very curious case of a model which was proposed by Vasquez with much fanfare, where they said that, look, biological networks, at that time it was believed that many biological networks are scale free. So they asked, okay, how do biological networks become scale free? Preferential attachment doesn't seem to be the right way. Why should one molecule decide to have interactions with a molecule which has already lots of other attachment, interactions? So could there be other reasons? So they proposed that, look, there could be something like a duplication and divergence, where you have some target protein which have interaction with lots of other things, and then the genome is, let's say, at some evolutionary point of time duplicated. So now there are two regions of the genome which are actually expressing the same gene. Okay. So now, because there is less pressure, evolutionary pressure for this gene not to be mutated, let's say it mutates a bit, and so therefore its binding affinity to, let's say, this particular element is reduced, but its binding affinity to some other new molecule is increased. So now you have a divergence. Okay. So in this mechanism, you can generate some network, and the claim was that this is also going to give rise to a scale-free distribution, albeit with a different exponent. Okay. So I used to happily talk about this to my systems biology class until there was this PhD student who wanted to do some what do you call end term project, and without thinking I said, okay, so end term projects are supposed to be done in just a few weeks. Okay, so there's no way you can do something original. So usually I just ask them to reproduce some or other paper. So I just very not even very absent-mindedly told her, oh, why don't you reproduce the scale-free nature of this distribution? So she was a very conscientious student. Right? So she disappeared completely for weeks. So after a while, I see her in the corridor, and I said, hey, why don't I see you? So she said, sir, I've been trying my best to get this scale-free degree distribution, but I just can't seem to get it. I don't know what I'm doing wrong. Can you see my program? So I usually hate to see someone's program because it's hard enough to read my own program, let alone someone else's. But I did the next best thing, which is I got my student to look at her program. Okay. So then the student and she kind of put their heads together, and the student comes back to me and says that there's nothing wrong with her program. So so he said, let me write my own program. Okay. So he wrote his own program, and he saw exactly the same thing that this girl was seeing. And so then I said, oh my God, I mean, what's going on? So then we tried lots of ways, and we found that actually the duplication divergence model does not show scale-free degree distribution at all. So again, what they did was they took a best case scenario, just cut it along the right thing, like a few decades, where it seemed to show almost a straight line, and just published it. Okay? So you need to be very, very skeptical about this report. So the one lesson I learned was, don't take any of these reports at face value. Okay? Someone might claim that this model shows scale free, but it might just be, they're just selectively showing certain results, and then, doing some, gradual jigging to actually show you what they want you to see. All right? Okay, so I am essentially out of time. I just wanted to tell you then very briefly what I would have told you had I had more time, again. So, which is that you can also look at how do networks differ when the nature of the links themselves are different. Okay, so some could be positive, some could be negative, and so on. So a very famous example of this was given by the the Gestalt psychologist Fritz Heider, who was working in the middle of the last century. So he basically wrote this very influential paper in 1946, where he basically said that the simplest non-trivial social organization is a triad of individuals. Okay? So imagine you have got three people, Om, Pradeep, and Zina. Okay? And you can actually try working out how the group dynamics depends upon the relative sign of the interactions. So let's say Om and Zina are friends. Okay, so this relation is a positive interaction, and Pradeep and Zina are also friend, positive interaction. But for obvious reasons, Om and Pradeep are enemies. Okay, classic, this is the plot of so many Hindi movies and romance novels and so on, right? So what you have, and why is this interesting? Because this is a recipe for tension, right? If all of them were friends, okay, who cares? Okay. So the question that Heider asked was that, is this stable? Okay. Is this something that can last? And he said, no. So there are certain kind of triads which are sustainable, and certain other kinds of triads which are unsustainable. Okay. So the sustainable triads are where, so if they're all positive, all friends, everything's hunky-dory. Suppose you have a situation where Om and Pradeep really like each other, but both hate Zina. Very unlikely, but let's say this happens. No problem, right? Because they just both avoid Zina. They just do their own thing. Okay. Similarly, in the other cases here, Zina and Pradeep are friends, or Zina and Om are friends, and both hate, like in this particular case, Om, and in this case, hate Pradeep. Again, very sustainable, right? Nothing's much going to happen. But if you have a situation where, let's say, this classic love triangle situation where, two people, one person likes both people, but those two people are hating each other's guts, then you have an unstable situation. And you can also have a situation where each hates the guts of the others. Okay. Again, pretty unstable, because, you hate, so Zina hates Pradeep and Zina hates Om, and she knows Om and Pradeep hate each other. But the thing is, who do you hurt most? Because of course, if you hurt Pradeep, Om would be very happy, right? You don't want to make Om happy, right? Okay. So basically, you have here no balance, and here you have balance. Okay. So what would happen here is that, so Heider said that in such situations, these unbalanced triads would end up becoming one of these balanced triads. So for example, you could say that friend of my enemy is my enemy. Okay. So let's take this one. Okay. Zina likes Pradeep. What am I saying? Zina likes Pradeep, but Zina hates Om. Okay. So Zina keeps telling Pradeep, don't go around with Om. Pradeep doesn't listen. And so finally Zina says, enough is enough. I'm not going to see you anymore. Okay. So it becomes this, okay? Or you can have enemy of my enemy is my friend, okay? So let's say Zina hates Pradeep and Zina hates Om, but maybe she hates Om more, okay? So she decides to form a coalition with Pradeep to basically get at Om, okay? All right? So you basically go from unbalanced to balanced situation. So this was, of course, a very qualitative way of looking at things. And then two mathematicians came into the picture. So Frank Harari, I think you might have heard his name if you have read some graph theory. Harari has this basic textbook on graph theory. So Cartwright and Harari wrote a paper very surprisingly in Psychology Reviews, and two mathematicians writing a paper getting published in Psychology Review won't be possible today, I can tell you. So, so they generalized this Hyder theory mathematically to n nodes, and they found some very interesting results. So they said that, look, in a balanced network, every closed loop has to be balanced. So what does a balance mean? It means the product of the signs has to be positive. Okay? So if you look at it, you will see that the product of each of these things, signs, is actually positive. Plus into plus into plus is plus, plus into minus is plus, minus into plus is plus, and so on. Whereas here all of them are negative. Okay? Minus into minus is negative, minus into plus is negative, and so on. Okay? Moreover, they showed that, sorry.
So can the loop break? Like the loop that you showed that the loop that is not balanced, can it break? Like?
Oh, if you, yeah, you can make it zero, but usually like you're talking about complete graphs. Okay? So the other thing they showed is that if you have a complete graph, that is where every node is connected to every other node with some link, either positive or negative, then you can show that if each triad is balanced, then automatically the network is balanced. So if you can show that all the 3 cycles are balanced, you don't need to go and show that 4 cycles are balanced, 5 cycles are balanced, 6 cycles are balanced. The fact that all the 3 cycles are balanced already proves that all the other cycles will be balanced. Moreover, in a balanced network with positive and negative links, you can always segregate out the network into 2 parts, into 2 groups, such that within each group, everyone has a positive relationship with each other, but between the 2 groups, everyone hates each other's guts. Okay? So this is a outcome of a balanced situation. Okay? And you can actually study such balance in real networks. So this is the network of international relations at the height of the Cold War. So these are like the links correspond to various military treaties and alliances in 1962. And you can see that it is a modular structure which actually corresponds to NATO, Arab League, Organization of African Unity, the Warsaw Pact, and the Organization of American States. So there's a very interesting study by Redner who showed that if you look at a similar network just before the First World War, you realize that just prior to the First World War, there was an enormous rise in the loss of balance. And their claim is that you can understand conflicts as basically ways of resolving lack of balance. So, you have a transition from no balance to balance. In the case of countries, this typically takes the form of conflict. So the more that the system basically deviates from balance, the more the likelihood of conflict arises. Of course, it's a hypothesis, but it's a very appealing hypothesis. So physicists, of course, structural balance means something else. It means lack of frustration, and the lack of balance means frustration. So, this is this classic case of, ferromagnetic spins, ferromagnetic interactions. So everything is hunky-dory. But if you have negative interactions in a triad, then of course the problem is that if this link is satisfied, you have a problem with what will happen here. So if you do it for an entire lattice, you can find that not all the links can be satisfied, and you end up with a rugged energy landscape. So, people can ask the question that what about other networks? Do biological networks show balance? So there is some evidence that, for example, the brain can be segregated into 2 groups of regions where if one is activated, the other is always inactive. And so, maybe the brain is also structurally balanced. But you can ask, okay, how is balance achieved? Some of my students actually worked on this idea that maybe learning is one mechanism. So learning in the sense of head, that is 2 neurons when they fire together, their synaptic strength tends to be increased. So this can actually if you apply it to a spin network, this Hebbian rule, you can actually show that it can go from frustration to unfrustrated system. Now, I'm completely out of time, so let me just go to my punchline to say that quite surprisingly, one of my students, Chandrasekhar, showed that you can actually use this concept of balance to see some order out of this chaos of financial markets. In particular, he was interested to see, is there a signature for systemic risk? Okay, so what is systemic risk? So even though markets do a lot of up and down, there are two primary events in which the chaos in the markets actually had an effect on the real economy. And these are the 1929 great, actually it should be depression, sorry, not recession, and the 2008 Great Recession. Okay? So the question was, can we actually, by looking at the network of interaction between stocks, somehow see that something very special happened during these two periods? So we were lucky because one of my collaborators had just bought this data set from New York Stock Exchange where he had the daily closing prices of all stocks that were traded in NYSE from 1925 to 2012. So this is almost a century worth of data. So my student Chandrasekhar, okay, I had some stuff on random networks and random matrix theory, which I thought would nicely relate with what Herbert was talking about, because we also actually use the eigenvalues of random networks in our work. But since I don't have time, I'll just flip across to say that if we reconstruct this correlation from the correlation of the stock price movements, if we construct the interaction network of the stocks, you can see the details in the intermediate slides. And if you don't, if you find it very forbidding, you can always write to me. And I'm also given this paper as a reading material today. So you can also look up the paper, which is kind of self-explanatory. You find that in normal periods, there is not that much interaction between the stocks, but this changes during this, events where systemic risk event starts happening. So this is in the middle of the Great Recession, and this is just prior to it. So you might say, okay, one can look at connection density, number of negative edges, clustering, but none of them are actually showing all that many, okay, so there are some changes, but if you show it to someone, they will say, okay, so what, and you can look at, core periphery analysis. So typically, you do find that the degree and size of the cores increase during crisis, but again, it's like a qualitative difference. So then Chandrasekhar kind of, just threw the kitchen sink on this, and he said, let me just measure everything. And he suddenly found that structural balance is a very, very robust indicator. So if you look at the balanced triads and the unbalanced triads in these interaction networks and compare it with what you would expect from randomized networks, you find that exactly during the crisis, 1929 Great Crash and 2007-8, you have the appearance of unbalanced triads. And you don't have appearance of unbalanced triads any other time. Okay? So this actually is a very, very interesting, kind of conjecture that could actually frustration be an indicator, or increased frustration of the system be an indicator of the systemic risk of a complex system. The unfortunate thing is we have no mechanistic explanation for this. We have tried lots of things, but this is an open problem. That exactly how is frustration leading to this rise of systemic risk? It's a nice empirical observation, but we would really like to know how this is actually coming about. So it's an open problem if you're interested, think about it. So let me conclude by giving out my last assignment, which is to do with this structural balance in networks that I talked about. So what I will do is, since I won't be around in today's tutorial, I will actually share with the organizers the answer sheets of both this one and the previous one, so that you can work it out yourself and then compare with the answer sheets that I will provide. Yeah.
So this, the appearance of unbalanced triads in the previous slide, does that have predictive power? Can you use that to prevent future recessions?
Wouldn't you like to know? Yeah, no. So if you have noticed something, the devil is in the details. We have to see, in order to construct the interaction network, you need to have enough data. Okay. So if you try to construct correlations from data sets which are smaller than the number of stocks, it turns out that these things are identical to just noise. Okay, so that's where this random matrix theory comes about. Okay, so you can look at the eigenvalues of the correlation matrix, and you can show that if the data set is too small, then if you destroyed all the correlations, so you shuffled the matrix and then again drew the eigenvalue spectrum, they'd be identical. So that means you can't actually tell noise from signal. So the data set actually has to be much longer. Okay, the longer it is, the more accurate it becomes. Okay, so you need to focus on the deviating eigenvalues from the bulk spectrum, which is actually identical to that of a noise matrix. So what we do is we use this eigenvectors of the deviating eigenvalues to actually reconstruct the group interaction network. So this is something I just skipped through, and that is what makes real-time prediction so difficult, because you need to have let's say years worth of data in order to be able to see how the systemic risk is actually increasing. Okay. So it's kind of not predictive, because by the time the systemic risk event actually breaks out, so you'll be probably only be able to say at that time, okay, so this is something which is happening. Okay. So yeah, I mean, we would dearly love to make it predictive, but unfortunately, data, the problem of data is where we are hitting a roadblock.
And one more question on the psychological review papers.
Yeah, Hiders or the Cartwright Harari.
There you said that the full network is balanced if all the triads are balanced. How do you mathematically define the stability of the full network? That's one question. And
No.
Is the condition of every triad being balanced also necessary, not just sufficient?
Okay, so when I say a full network, I mean a connected network. So that means every node is connected to every other node. Okay, it could be positive or negative. So the question is that if you don't have that condition, then you can't just look at only the triads and conclude the balance or otherwise of the full network. Okay, but if it is connected, then you can show that if all the triads are balanced, automatically all the 4 cycles, 5 cycles, 6 cycles would also be balanced.
So you're basically taking the product of the signs and all the...
Yeah, I mean, it can be easily shown. Okay, and the thing is that if a triad is unbalanced, if even a single triad is unbalanced, by definition, the network is unbalanced. Okay. Okay. Sorry about that. It's 20 minutes past time.
Fascinating set of lectures, and also I think reminding the students that you are in the right field because physicists are the greatest. So
oh, okay. Sorry, I forgot to mention one thing that. So Ritam actually has been visualizing this interaction networks, and he's finding that the network is becoming almost a click, which already tells you something about the success of your school. Okay. Yeah, I mean, you have sent me the image. Let me see. Okay, so I'll just try to see if I can show it to you. So sorry for keeping you from lunch a little more, but I think this would be interesting. This one, right, Ritam? Okay, so colors represent institutions, squares represent men, circles represent ladies, and as you can see, a strong core has developed. It will be interesting to see how much reciprocity is there though. All right, so you can already declare your school a success to your funding agency. All right.
Last lecture on this topic. So today I wanted to talk about noise in chemotaxis. So till now we were discussing the phenomena of chemotaxis and the signaling pathway that inside the cell which governs, which makes the cell behave in that way. But today I will talk about what is the role of fluctuations, role of noise in that network. Now, initially, I mean, when people started the study of chemotaxis, people were mainly using a population of cell. Now, it was commonly accepted that if you put a population of cell in an environment which is homogeneous, no gradient, nothing, and if you assume the cell is all the cells have already adapted to the environment, then you would expect the tumbling frequency to be constant, not dependent on time. If you would like to go one step back, look at several different important protein concentration inside the cell, you would expect that it is constant. It is not on an average, it is not changing with time. So, but however, if you manage to look at the output of a single cell, let us say you don't average over the cell population, just focus on one cell and look at its run tumble switching trajectory. Then you might find it would be more noisy than the population, right? And so then particularly when about in 2000, early 2004, around that time, when the single cell measurements became possible, that people could actually look at the behavior of a single cell, then people also asked the question that the fact that it is noisy, how does it affect the behavior of an individual bacterium of E. coli in a homogeneous environment? Also, people started asking what might be causing the noise in the whole network. So, in 2004, Korokova and their collaborators, they published a work where they looked at, they just focused on one single flagellar motor, and they looked at the time series of its counterclockwise and clockwise rotation. So, this is the experimental data. And you would expect that, and it is homogeneous environment, no gradient, nothing. So you would expect that if the switching rates are constant, then you would expect that the time interval between two switching events, that will be following an exponential distribution. So here they have plotted the clockwise and counterclockwise residence time distribution. Although for clockwise they found more or less an exponential, for the counterclockwise, which is for the run duration distribution, they found it is not an exponential. In fact, when they plotted in a log-log scale, they found it is, I mean, there is a large stretch which can be fitted to a power law, and the exponent is roughly 2.2. So then they assume that it is happening because of noise present in the network. So then you might ask, what is the, okay, in the network there are a lot of steps, activity switching, phosphorylation, binding to the flagellar motors. Also you have this adaptation, methylation, demethylation reactions. So out of all these steps, of course, there is stochasticity at every step, okay? Because when we write the rates, those are average rates. So out of all these steps, what could be the most important source of fluctuation? Then the natural choice was that it must be coming from methylation demethylation cycle. Why? Because these are extremely slow processes. Methylation demethylation reactions are 100 times slower than any other reactions which are taking place, at least 100 times slower. So therefore, if there is any fluctuation in the methylation level, it enters the system as a slow noise. Now, if there is some variable which is changing very fast, and then if it has some noise, then you can easily integrate it over. But if it is a variable which is changing very slowly and on top of it, it has a slow noise, then it gets very difficult to, the downstream processes cannot integrate it over. So the slow noise you cannot get rid of so easily. So why, and particularly given the huge number of receptors, few hundred, and very few number of enzymes which are responsible for methylating and demethylating them, you might expect that the methylation level of the receptors, if it has some noise because of these very slow processes, it will be important. So to check that, what they did, they increased the concentration of KIR enzyme. So starting from a wild type E. coli, they considered some mutant strain where KIR enzymes are systematically overexpressed. And then they find that as they increase the concentration of KIR molecules, the power law behavior goes away and it begins to look like an exponential. So this also, this is an evidence that indeed it is coming from this methylation part of the network. When you increase, when you have more and more KIR molecules, then the reactions are a little bit faster. Each receptor doesn't have to wait a very long time in order to get some attention from an enzyme. So therefore, then it looks more like an exponential. To further answer these, understand these results, there was a theoretical work done by Tu and Greenstein in 2005. So they had shown that they considered it theoretically. They had said, okay, I am not worried about any biochemical pathway, nothing. I will just consider the clockwise and counterclockwise state of the motor as a two-level system. And the transition rate between these two states will be fluctuating. These are states whose energy gap between the two states is showing correlated fluctuations in time. What is the reason for thinking so? Because you see, if methylation, it is ultimately the concentration of these phosphorylated QI molecules which are causing the cell to tumble, right? Now, if this QIP molecule fluctuates, because it is ultimately coming as an output of this signaling network which is noisy, if QIP concentration fluctuates, then there would be different switching rate between counterclockwise and clockwise bias. So this is a typical, this could be some, let's say, temporal variation of QIP concentration. So what they did, they considered this equation. It is the time evolution equation for QIP. Y0 is the average value. So this is the relaxation part, and then there is a noise. And they had shown indeed that when they increase the strength of the noise, they do find a power law behavior. So for example, here this black curve corresponds to zero noise. It is in log scale, it is actually an exponential. But as they increase the strength of the noise, this red, green, blue, it is converging towards a power law. Okay. So, they found the exponent to be close to 2, which is not very different from 2.2 observed in experiment. Yes. It is a?
Eta is also a power law, right? Is it power law, eta?
Eta is a Gaussian white noise. The
eta is a Gaussian white
YP
noise.
as a result has a correlated fluctuations.
Okay.
Eta is a Gaussian white noise. Okay. And the strength of eta is given by these numbers.
So you're just looking at the residence time distribution.
Yes, residence time distribution.
Does it become like in a why is it power law with Gaussian white noise, is it?
This is Gaussian white noise. If there is no noise, then it is an exponential.
Right,
but when you have stronger and stronger noise, then it becomes like a power law. So it is possible to have, they also have some theoretical calculations. They can also show it, but I don't have it here.
No, because this looks just like overtime, in a trapped Ornstein-Uhlenbeck process.
Ornstein-Uhlenbeck, yes, Ornstein-Uhlenbeck process.
But why
yes.
is that residence time is, I thought, still exponential?
Then you are, that quantity is slightly different, right?
No, yeah, so this is some function of yp. Okay, this, I mean the switching rates, yeah, I should have included gy perhaps, I don't remember its form right now. I mean, this switching rate, switching rate depends on the free energy difference between them, which is a function of this QIP concentration.
Oh, that also depends.
Yes, yes, yes. Sorry, I should have included the GY term, which I don't remember right now, but yeah. So they also have some calculations where they show that they expect indeed this exponent too. Yes?
Sorry, I did not get explanation. Why is it different from Ornstein-Uhlenbeck result?
No, it is not different. This QIP follows Ornstein-Uhlenbeck, but what actually matters is the transition rate between these two states, which is a function of QIP. These rates are given here, e to the minus delta G y by kBT.
Aha, I see.
So Gy is a function whose form I should have included here.
Of y, okay, thank you.
Okay, so this, yes.
What is the distribution of k plus and k minus? I mean, given this, probably there is a distribution of k plus and k minus, right? So what kind of distribution of k plus and k minus will give?
The switching rate distribution.
Yeah, right.
Yeah,
I mean,
so
this is what is happening, right?
That was not calculated. I mean, the way it was done is you read off the instantaneous concentration of yt and calculate this rate function, and you then switch according to these rates. But it should be possible to, yeah, if you know the...
Basically, you need very small k, right, so that it stays for a very long time, right? I mean,
you need very?
Small k so that whatever the state, I mean, lives for a long time, basically. The rate, when the rate becomes very small...
Oh, you mean because it is staying for a long time? Okay,
yeah,
okay, yeah.
K plus, yeah. So I guess given this and given the z, you can finally express in terms of the distribution of k plus and k minus.
Yes. Now, of course, that should be possible, but they don't calculate that in their work. Yeah. Okay, so then after this work, it was kind of people, I mean, kind of realized that this methylation noise is really important and it has to be taken seriously. So then the natural question to ask was, how this noise is affecting the chemotactic behavior of the cell? Is it making the cell less efficient in tracking the nutrient? What is happening? So to answer that question, first it is important that we quantify performance. What do we mean by performance? One way to quantify performance would be the chemotactic drift velocity, which measures how fast the cell is able to climb up the gradient. Remember, this is different from run speed. Run speed is fixed. But as we said, that favorable runs are elongated, unfavorable runs are shortened. So therefore, after lot of run tumble events, the cell will develop some net drift motion. It is that drift velocity we are talking about. Now from often the accepted definition of drift velocity is, I mean, from a run tumble trajectory, you can extract drift velocity in different ways. Often people look at net displacement in a run divided by the mean run duration. This is the expression for drift velocity. So clearly, if the drift velocity is large, that means the cell is quickly climbing up the hill. So that should be considered as a good performance. Another possible measure for performance is, this quantity is called localization. This is how it is defined. Integral dx, px, cx. Px is the position distribution of the cell in steady state, and cx is the nutrient concentration. So if this quantity is large, you see this integral will be large only if both px and cx are large for any x. So if it so happens that for most of the x's where px is large, cx is small, or when px is small, cx is large, then it is localization value will be small, and in fact that is not a good chemotactic performance. Where you have more food, there are very few cells present, and vice versa. So therefore, this is also another, this tells you how the cell is sampling the nutrient molecules. So both drift velocity and localization, if they are taking high values or something, then you say that, okay, it is a good performance. So the question is, how methylation noise affects this performance? to answer this question, in 2012, Floats and their collaborators, they did some theoretical work where they had shown that if they consider a shallow nutrient gradient, that weak gradient, then there is the drift velocity as a function of the methylation noise strength shows a peak. So starting from very low noise, if you increase the strength of the noise, drift velocity increases, reaches a peak, then goes down. And localization first does not change with noise, and then beyond some value it also goes down. So therefore, there is some value of the noise strength which seems optimum for the cell. Drift velocity is maximum and localization is also not too small. And they now notice that this is a surprising result, because you would typically expect with noise performance will be getting worse, because if the intracellular noise is too much, the cell should not be good at processing the signal it is receiving from outside. So the fact that it decreases with noise for large noise is not surprising. What is surprising here is the increase of this drift velocity for small noise. So what is causing that? So to explain these results, they said that when as noise increases, longer and longer runs become more and more probable. And it is these long runs which are actually contributing most towards the drift velocity. And when you increase noise, these long runs become more probable, and that is actually causing enhancement of drift velocity. But what we had shown in a later work, that this is not the complete story. In order to understand this effect, you have to perform a detailed analysis of QIP level fluctuations in presence of signaling noise. So I will not go into too much of details, but let me just say this much, that okay, we considered a ligand concentration, linear concentration of nutrient profile with a positive slope. So Cx increases with x, and we considered a one-dimensional motion of the cell. It can go either rightward or leftward. Rightward in this case would mean uphill, and leftward would in this case would mean downhill. Now, suppose you are looking at a run, okay, and of course this run tumble things are happening all the time. Now let us say a particular and QIP concentrations are also changing, right, because ligand concentration is changing, methylation, demethylation reactions are happening. So here I have plotted, let's say delta Yp be the net displacement in a run which start with some specific value of QIP concentration. I call it Yp. Okay? Net displacement in a run which starts from some specific value of Yp, and then I plot that quantity as a function of Yp. So what we find, for small Yp this shows a negative peak, and for large Yp this shows a positive peak. The positive peak is not so visible in this scale, so I have plotted it, a zoomed version in the right panel. Now, if it is a negative peak, that means net displacement of the cell in a run which starts with small Yp is negative, downhill. This behavior is detrimental for chemotaxis. Of course, I mean, there should not be any confusion. If you want to find out the chemotactic drift velocity, then you have to do a weighted average over all values of Yp from this data. And of course, that will be positive. This measurement does not tell you that chemotaxis is not happening, the cell is accumulating in a region where there is less food. Because when you perform a weighted average, these very low values will be towards the left tail of the distribution. So they occur with less weight. So the ultimate value of the drift velocity remains positive. Nevertheless, because of this part, it actually brings down the value of that sum. Because here the displacements are negative, the total displacement when you calculate, because of these parts, the displacement is coming down, the value is coming down. So this behavior, this is why we call this behavior is detrimental to chemotaxis. But notice that for these are different noise strength, okay, the lambda. As I increase the noise strength, the this behavior is getting shifted to lower and lower values of QIP. So what I am trying to say here is QIP level of course fluctuates. There is a threshold value of QIP below which the cell behaves in a way which is not good for its chemotactic performance. But the threshold keeps shifting with noise. The threshold gets shifted to lower and lower values as you increase the strength of the noise. So this is responsible for the noise induced enhancement of drift velocity. Okay? Of course, it works only up to some point. If the noise is too much, then it is too noisy, the performance goes down. Now, however, recently there were some experiments, and in fact these two groups, Colleen and their collaborator and Kickstra and their collaborator, these two groups performed experiments where they have found even when there is no methylation, even then they are recording important fluctuations in the cell. So what they did a freight based experiment, and in the left panel they have plotted the power spectrum of the activity fluctuations of the cell for a cell where no KIR or KIB enzyme is there. So the methylation demethylation cycle is completely turned off. For this mutant strain, therefore you should not expect any noise. If the main noise is coming from methylation and I have switched it off, you should not expect any noise. But they find, look at the black curve, they find that there is a significant noise still present. And when they compare it with the wild type cell where no deletion, where methylation demethylation cycle is there, the noise is actually quite comparable. You see the values here, this is 10 to the minus 2, it is quite comparable. Look at the black curve. So they found that whether there is methylation or not, the cell still records some important fluctuations. So the conclusion therefore is, there is another important source of noise apart from methylation. And they found that when they disrupt the receptor clustering, then the noise is gone. So this red curve in both the cases, it shows that when they use some proteins to such that the cooperative interaction between the receptors is disrupted, then they are not forming clusters and then the noise is gone. So from here they concluded that receptor clustering is an independent and equally important noise source in the pathway. So the question we are asking is how this newly found noise source affects the chemotactic efficiency. So yes.
Last experiment was this single motor, right? Like okay, but if you just look at the, if you don't focus on the motor, just look at the run length or run time. So is it power law, like experimentally?
It is power law. That's what people believed. That although most of the studies were being done on tethered cell and looking at the
but like if you just
output,
look at a bacteria, wild type bacteria on this thing and just measure the...
Yeah, it was believed to be a power law.
But then the power 2, is it?
Power 2, 2.2, something like that.
Okay. No, like, okay, 2.2 is okay then still. Because you also say that there's a characteristic time of 1 second, right? I mean, if it is 2, then there is no characteristic time, right?
No, that is right. But you know, there is a cutoff also. It cannot go on.
Okay.
If you see that, I mean, it ends. I mean, it doesn't continue forever. So
okay.
There is a cutoff which actually makes it finite.
Okay.
Any questions? So now these experiments show that receptor clustering is an important source of fluctuations, and we are asking the question how this newly found noise source affects the chemotactic efficiency. So here we plot, this is within our simulation, the activity distribution for different cluster size. So we vary the cluster size. We consider this all or none model, which I described yesterday, and we play with the cluster size. So as you can see that when cluster size increases, then the distribution becomes wider. In fact, if you plot the variance of these distributions as a function of the cluster size, you find almost it's a straight line. Now, if you look at it this way, then actually it is not so surprising because the number of receptors in the cell is fixed. If you have smaller clusters, then that means there are many clusters present. And then each cluster has one activity. All the receptors within a cluster has the same activity. So the final activity you are calculating after averaging over a large number of teams. Compared to that, if there are few large clusters, then the final activity is being calculated after averaging over only few number of clusters. So that increases the fluctuations. In fact, although clusters are not completely independent here because they share the enzymes, etc., they share many resources. The receptors belonging to two different clusters are not completely independent. But nevertheless, we found that a variance still scales with the cluster size. So although these experimental papers do not put it that way, but I think it is easy to understand why you would expect that larger clusters would give rise to strong fluctuations. So how does it affect the performance? So here we plot localization. Yeah. So what we have done, we have used this type of an attractant profile. That Cx is some constant, it is a linear function of x, and then if x naught is large, that is if I am using the weak gradient, then you would expect px, the position distribution of x, would also be more or less linear. And the slope of the distribution then acts as a good measure for the performance. You can imagine if the slope is steep, then that means the cell has a strong affinity for the part where the concentration is large. On the other hand, if it is almost flat, then the cell is hardly distinguishing between nutrient rich region and nutrient depleted region, so it is not a good performance. So the slope is a good measure, and we find the slope as a function of receptor cluster size shows a peak. The bottom panel is for drift velocity. So we have measured drift velocity in two ways. One is you can measure net displacement in a run and divide it by the run duration. Another is you can simply observe the cell for a long enough time interval and measure its net displacement in that time interval. The values are different, but both the quantities show a peak as a function of the cluster size. You could also find out some slightly more, yes?
So you had this formula, the px-cx integral. So what was that one?
That was called localization.
No, like where does the derivative of c appear? Because finally the derivative of c which matters.
Derivative of c will directly affect the drift velocity.
So you can write down the drift velocity in terms of the derivative of c.
Drift velocity, you can drift velocity is actually proportional to gradient of c.
Ah, okay.
You can do, there was a calculation by Dijon which shows that.
Okay.
But here I am just looking at the static just how steep it is. I would expect a linear profile, how steep it is. Of course, the slope, if you look at the slope, that will be a function of the gradient also, because it is proportional to c. So if you make it steep, px would also be steeper. So this is some slightly more generalized way to describe a performance. I could say that chemotactic performance could be described as the ability of the cell to distinguish between a good region and a bad region. So suppose how the cell behaves, so to put it this way, the differential behavior of the cell when the nutrient level in its environment goes up or down. So in other words, suppose a cell is running uphill. How long does it take to tumble for the first time? So you catch the cell in a time when the cell is running uphill. What is the mean first passage time to tumble? You catch the cell when it is running downhill. What is the mean first passage time to tumble? And the difference between these two times is a measure of how good the performance is. So so here we have plotted this quantity, we call it tau r minus tau L, and we find that even this quantity shows a peak. So this differential behavior tells me if there is no difference, then of course it is not distinguishing between an uphill or downhill run. So that is not a good way to track the nutrient. And interestingly, this type of description can also be used for a tethered cell when there is no run tumble motion at all. So all you have to consider, you consider a tethered cell and you just ramp up the nutrient concentration in their neighborhood. And to compare between these two, you can even consider ramping up at the same rate at which a swimming cell going uphill would face the gradient. So, you suppose you consider a tethered cell, the motor was rotating in the counterclockwise manner. Then you ramp up the nutrient concentration and wait how long does it take to start rotating in the clockwise direction. Do the same thing for a ramp down nutrient concentration and take the difference between these two quantities. So this was the data for a tethered cell, and even that shows a peak as a function of cluster size. Yes?
Yes, ma'am, like you can go back like one slide. One more. Yes, ma'am. So, like, if you look here, like the position of the peak is also like shifting towards left. So, like, is this something like trivial?
Position of the peak shifts slightly, yes.
Yes,
it has some I forgot that now. The variance is increasing with n, and you are saying the position of the peak is also shifting slightly with n. I have to look it up actually. I don't remember the explanations right now. It was we were able to, I think, calculate the activity distribution. No, this we could not calculate analytically, but position was slightly changing with n. So, although it is the dependency is mild, I mean this was 10, this was 150, but still there is some dependence. Yeah, sorry, I don't. Yeah.
Is there some connection with giant number fluctuations that is seen in active matter? Is this
giant number that? So it is more simpler. It is just like central limit theorem. Variance scales linearly with the number of teams over which you are averaging. That's all. Yes.
I had a question with this. When you were like people were studying like you remove this.
Methylation
and
demethylation.
demethylation. Then how is this bacteria? Now there will be low activity inside, and so it will be like running.
No, there will be activity. Yes, there would be any adaptation.
Okay, yeah. So
and also here, I mean, in these experiments, they were not worried about chemotactic performance at all, because there was no gradient. It was an homogeneous environment. They just considered a methylation deficient cell, and then it was intention done that. Look, there is something else. So even if I turn off methylation, there is still fluctuations. That was the only point. Okay. Of course, these methylation deficient cells cannot function normally. No adaptation. You are right. Any other questions?
So you said, I think 2-3 slides down, that this difference between mean first passage times to tumble is a measure. Is that significantly different from the mean run length?
Not too much different, except when you consider mean run length, you consider one tumble till the next. But here the quantity is slightly different. You are catching the cell anywhere during a run, and you are waiting the mean first passage time to the next tumble.
Okay, and this is different for uphill and downhill.
This is?
Different for uphill and downhill conditions.
This has to be different. If it is same, that means you are not able to distinguish between an uphill and downhill run. So basically here what we are measuring the how differential response the cell shows when you put it in a good region, good environment versus in a bad environment. Any other questions? Okay. So, now we would like to understand what is happening here. So, we will see that this optimal size of the receptor cluster is a result of competition between two important modules of the signaling network, sensing and adaptation, which we have learnt about in the last 2 lectures. So, the total free energy, can this fan be made faster, or it is the only speed in which it moves? Okay, it's not possible. Okay. No regulator, nothing, right? Okay, okay. Thank you very much. So, if you remember, the free energy difference between the active and inactive state of a cluster had 2 parts. One depending on methylation, another depending on the ligand concentration. Now, as the cell is swimming uphill or downhill, here I have gradient, right? The ligand concentration is changing everywhere. When the cell is moving up or down the gradient, the ligand concentration is changing, so ligand part of the free energy is changing clearly. And that change is proportional to the cluster size, okay? Because it is just getting multiplied by n, if you remember the all or none model which we had derived yesterday. So therefore, it is actually nothing but signal amplification which I am talking about here. As n increases, as the cluster size increases, the input signal is getting amplified more and more. In the language of this model, it would mean that the change in ligand concentration is proportional to n. It is just scaling with n. So therefore, for starting from a small n, when you are increasing the cluster size, then the input signal is getting amplified, uphill runs get elongated, downhill runs get shortened. This gives rise to a better performance. This is expected. But when n is large, their experiment and also our subsequent simulations show activity fluctuations increase. It is like a large cluster, many receptors there. All of them suddenly flip their activity. So there would be a large change in activity. So these things are happening all the time. Activity is becoming too high or too low. And then the adaptation module becomes very, it gets triggered. So there are a lot of methylation, demethylation reactions which would now take place to bring the activity back to normal. And therefore, the free energy F will now be controlled by the change in Fm rather than change in Fl. When the activity fluctuations increase, it becomes less sensitive to the ligand variation from its environment, and it will be controlled by, you remember, the transition between active-inactive state is ultimately controlled by the free energy between the 2 states. What we are saying here now is, even though n is increasing, the activity fluctuations will be so much that change in Fm will be very large. To check this, we have this, this is a typical, let's say we consider a particular cluster and we look at the time series of its activity, 1, 0, that is the active-inactive. So this is a typical time series when the cluster is switching between active and inactive states, and this is for a large cluster, okay? Here I plot for the same time series the corresponding change in the ligand concentration profile, and in this panel I look at the corresponding change in the methylation free energy, Fm. So you see Fm varies over a much wider range compared to Fl, okay? So therefore change in F is mainly controlled by change in Fm. Fl now plays a relatively minor role. So the cell becomes insensitive or relatively less sensitive to the ligand variation, and its performance goes down. So in this limit, it is, suppose I am now calculating the, to check it, I am calculating the probability of having a shorter uphill run and a longer downhill run. So they becomes increasingly likely. So suppose I explicitly calculate the probability that during a certain time interval, capital T, the cell shows a negative net displacement. What is the probability for this event? Of course, you see these type of events are not good for chemotaxis. Now I calculate the probability of this type of events. And this is how this probability behaves. With n, it first decreases, which means performance is improving, but then after an n, it starts increasing again. So now it is less sensitive to ligand variation, controlled by methylation. It doesn't mind, okay, shorter uphill run, longer downhill runs, who cares? I have to satisfy the what is FM part is telling me to do. Okay. These were mainly time series to consider a more average quantity, slightly average quantities. We look at this is the average change in FL and FM during first few steps of an uphill run. Now here, since I consider a linear concentration profile, change in FL will trivially be linear. But these discrete data points, they show the change in FM. So what exactly I am measuring? Suppose an uphill run starts now. I wait for 0.5 seconds, during which the uphill run is continuing, and I measure the change in FL and FM. So when the cluster size is small, you see that change in FL is quite large. But as cluster size increases, FM starts catching up, and finally for very large cluster size, it is much larger than the change in FL. Okay. So therefore, what we have shown here is enhanced sensitivity. So far people were talking about cooperativity is good, signal amplification is helping me to detect very weak gradient, etc. What we are showing that the enhanced sensitivity comes at the cost of increased biochemical noise, and which ultimately gives rise to an optimum strength of cooperative interaction or optimum size of the cluster. So here, this was something I mentioned also a couple of lectures back. So there was some earlier work, much earlier than ours. They also report an optimal size of the receptor cluster, but they considered a noisy input signal. And their idea was that when you have a noisy input signal, the noisy ligand environment, then when it is amplifying, the noise is also getting amplified, and therefore beyond a point too much amplification is not good. But we find optimality even in absence of any noise in the ligand environment. Any questions? Okay. So this was all for a swimming cell. So next we wanted to look at the effect of receptor clustering on some tethered cell. Most of the experiments are still being done on tethered cells. So this is my setup. I consider cell in an background in ligand concentration L0. Then suddenly at time t is equal to 0, I raise it to some value L1. Now I expect that in the pre-stimulus state, t less than 0, the cell was perfectly adapted to its environment. Even in the post-stimulus state, when it has readapted to its environment, the receptor activity and CW bias, these quantities have time independent average values for t less than 0 at t goes to infinity. Both are in steady state. But shortly after you give the signal, then of course these quantities will show rapid variation in time. We have discussed how they quickly decay, then adaptation brings it back up, etc. So far, most of the studies were focused on the long time relaxation to adaptation states, adapted state. And you see, based on what we have discussed also so far, we mainly focused on the fact that after long time it goes back to adaptation, at the adapted value. We showed that there is exact adaptation, etc. But what we wanted to look at is the short time behavior. Particularly, after you give the signal, it needs some time to reach this extremal value from which it will start to rise. We are asking how long does the cell need to reach this extremal response, and how to characterize the properties of the network at this point. This is very away from any kind of steady state we are talking about now. So we have been able to perform exact calculation in this to answer these questions. So I'll before I present the exact calculation, first let me show you the simulation data. So here I plot the time variation of average activity. By this look at the discrete points first, their time variation of average activity. So as expected, for different cluster size, average activity first decreases and then increases. And this left panel is for step addition of stimulus, right panel is for step removal of stimulus. Okay? And these continuous lines, I am plotting this quantity, 1 plus e to the f inverse average. You see, now that the ligand concentration has been suddenly changed and methylations are trying to catch up, the free energy difference between the active inactive states are now changing with time. Okay? And if both were independent, like in this case pre-stimulus state, they will be equal, because then it is kind of Boltzmann condition is holding, average activity is given by 1 by 1 plus e to the f. But now when both are changing with time, of course they start differing, except at the extremal point when they are intersecting again. This is true for all cluster size. This is true for both step addition and step removal of stimulus. So what is happening? It seems that temporarily, for this time being, momentarily, as if suddenly this equality holds, and then they go away again. Finally, in the very long time limit, I would expect the equality to hold again, which I don't show here. So this equality is generally expected when the system is adapted, but here nobody will say it is adapted. It is farthest from any kind of adaptation. Even then they are holding. And so we would like to now understand what is happening here. So it turns out it is actually, the reason is very simple. Let P N1T be the probability to find N1 active receptor clusters at time t. And I am constructing the time evolution equation for this probability. So I hope all of you are familiar with master equations, and yeah, this was discussed in detail in one of the lectures. So here, how can this probability increase? The system may have started with one less active cluster, and then one cluster has switched from inactive to active state. So this gamma, they give the total transition rate. For example, gamma 0 to 1 tells me the total transition rate from inactive to active state. Now remember one thing, that this transition rate depends on the free energy, right? Free energy between the two states. Now this free energy is a function of M and L, methylation and ligand concentration. Ligand concentration is not changing with time anymore. I changed it at t is equal to 0, I am not touching it. But methylation is changing. So therefore, you have to really sum over all methylation values, weighted sum, in order to get the total transition rate from inactive to active state or active to inactive state. So that is what I have done here. So this is the term where I started with one cluster less and one switched from inactive to active state. This will correspond to a gain. And this term where I started with one cluster more and the reverse transition happened, and these N1 plus 1, these are like between these N1 plus 1 clusters, any one can flip. So that's why I have to multiply it with this number. So this is the master equation. And then what you do, you multiply both sides with N1 and sum over all N1. Is any question? Yes.
So is this the same, the activity that you were talking about in the previous slide, is it, I'm sorry if it's a repetition, but is it the activity of the receptor?
No,
or
this is not activity. This is probability to find N1 active receptor cluster.
This is different from the
activity is average N1.
Okay.
When you that is what I have written here. When you multiply it with N1, sum over all N1, then you get DDT of average N1, that is the, when that you multiply it by the total number of clusters, that gives you the activity. So when you multiply it with N1, sum over N1, lot of terms get cancelled and you have this relatively simpler expression. And average activity is, as Adarsh was asking, average activity is nothing but N1T by N, and at time t is equal to Ta, the derivative must vanish, right? Because t is equal to Ta, where they were matching, that is the dAdt is 0, isn't it? So the derivative must vanish, and then that gives me this condition that At is equal to Ta must be equal to this. So this is a very simple explanation, but the result looks surprising initially. So it seems an equilibrium-like relationship holds between, equilibrium-like relationship holds between time varying activity and time varying free energy momentarily before they go further away again. We also looked at how TA, the extremal time, changes with receptor cluster size. And here also we find something interesting, that there is a minimum. So apparently TA decreases, reaches a minimum and then increases again. And so therefore it seems there is a special value of the receptor cluster at which the system reaches its extremal value at the shortest possible time. So to explain this result, we define this quantity Zt, which is the difference between the Boltzmann form minus the actual activity. And by definition, Zta is 0, because at t is equal to Ta, both these quantities intersect, they are equal. Now here I plot this, sorry. So first I wanted to show that for large n, Ta would increase. So let me consider this case of step removal. For large n, when cluster size is large, if you remove the stimulus, suddenly take away some attractant from the system, then the drop in free energy will also be large, because n is large. So then this rate, this becomes very close to unity. So if you look at Z, that would be Zt would almost be given by 1 minus At. So it means one active to inactive state transitions remain effectively blocked during this time. Immediately after removing the stimulus, activity becomes, immediately after removing the stimulus, active to inactive state transitions remain effectively blocked, and so therefore At can only increase during this time. It's okay, right? That's what you would expect, that if you remove the stimulus, activity would suddenly go up. So one kind of transition is being suppressed, another kind of transition is being favored. And as n increases, it takes longer for the system to restart the reverse transition. So here I have plotted this. You see, this is the, for different values of n, as a function of time, I am plotting the transition rate from inactive to active. And you see, as n increases, it remains stuck to unity for a longer time before it starts decreasing again. I mean, you see the tipping point where dAdt changes sign, that will be the other kind of transition is taking over. So far activity was decreasing or increasing. Now it changes its trend. So the reverse transition now takes over. And that takes longer and longer as you increase the cluster size. So therefore, Ta will increase with n for large n. Is this clear to everyone? Then for small n, we can show that Ta will decrease with n for small n. If for small n, there is no such thing. If the cluster size is small, no transition gets blocked. Both forward and reverse transitions are there. But the difference between them, difference between these two rates, the difference grows with n. As a result, Zt, the difference between activity and its Boltzmann form, it reaches 0 quicker. And therefore, Ta decreases with n. So we showed that Ta decreases with n for small n, increases with n for large n. So there is some intermediate n where it will hit a minimum. Everything I said can be translated if I don't touch n, but if I just play with the stimulus size. Whether I am adding 10 micromolar stimulus or whether I am adding 30 micromolar stimulus, that I can play with, and everything I said can be translated through. For a large stimulus, one type of transition will get blocked, and it will remain blocked that way as I increase the size of stimulus. For the other stimulus, the Zt, the difference between these two quantities will reach 0 quicker. And as a result, it means that if as a function of stimulus size also I should get a minimum, and that is exactly what we find in simulation. And this is some very simple prediction which can be tested in experiments also. So this was the activity. Then we could also do the same thing for tumbling bias. So this is tumbling bias we have plotted as a function of time for step addition and step removal. And here also we find there is an extremal value of, the tumbling bias decreases and then increases, and we identify TCW from there. And we can perform similar calculations here. Here QCW N1T is the joint probability to find the motors in the CW rotation mode with N1 active clusters at time t. So this is the joint probability. We write down time evolution equation for this joint probability. So that there are two different, remember it is a joint probability. So when we are writing down the time evolution equation, you have to consider two types of transitions when both these things can change. So these first two terms tell me CW or CCW, they can interchange back and forth. Then these remaining terms tell me the transitions which would change the value of N1. Both types of moves will actually bring about a change in this joint probability. And when we sum over both sides over N1, we get a simpler description. It is the probability to find the cell in the clockwise bias mode at time t, and this has this expression, okay? And in the extremal limit, when extremal time, when this time derivative is 0, both these things are equal. And indeed we find that for step removal we have plotted this data, that exactly, this is the comparison between simulation and the exact calculation. That exact calculation tells us that it is 4.3 plus minus 0.2 and 3.6 plus minus 0.2 for two different clusters, which is, sorry, I don't have the values here. Yeah, so the values can be, so this value was 3.6 plus minus 0.2, our prediction from exact calculation. This value was 4.3 plus minus 0.2, so both these things match quite well. And again, this equality is expected to hold only in the adapted state, but we are finding at this special time TCW also, there is a zero crossing. And in a similar way, this quantity also shows a minimum as a function of n, the cluster size. So most experimental, so just to summarize, most experimental and theoretical studies, they consider long time behavior of post-stimulus recovery. We show that in the short time behavior also there can be, you can do some exact calculations and find some important conclusions. Okay, so yeah, so the rest of the things, that's all I wanted to say. This is a shorter, yeah, I finished earlier. Okay, so any questions or anything, I'll be happy to answer.
You mentioned that as you increase noise, the localization stays constant and then it starts to decrease,
yes.
right?
In their work, in the work by Floor Settle, that's what happens.
Is it critically dependent on the setup? Because I guess we can have setups where if the noise is below a certain threshold, you sort of reach a deadlock. You don't get to the more optimum.
Actually it is, so since you asked the question, you see localization was defined as dx, px, cx, right? The integral.
Yeah.
Now what we find, its variation is rather slow. This quantity, its variation is rather slow. So when we repeated their work, we found that there is no saturation. Localization also shows a peak and then decreases. But its variation is slow, so maybe they mistook it for saturation and then decreases. But actually there is a peak. peak in localization also, just like there is a peak in drift velocity.
So depending on setup, you could have statistically significant.
No, it is not. I think we are using exactly their setup. So I don't think it is based on. I think they, because the variation is so slow, they might be. It may be that they did not look at it carefully.
So in the step initial condition, this translation between the cluster size and the step size, that's basically because the cluster acts as a gain factor, right? The cluster size. Do we see similar sort of behavior when we have gradients? Like, can we also interpret basically the cluster size in the gradient situation as additional driving?
So yeah, I mean, this is what I mean. When you say signal amplification, so the given signal is being amplified, but you could amplify a signal by actually amplifying it, right? I mean, put in more gradients, so it should be the same thing.
Then effectively all of these minimas that we are seeing, it means that as I'm increasing driving, I'm seeing a minima for my response time and things like that.
As I'm increasing driving, okay,
like there is an optimal driving.
Optimal driving, optimal amplification factor, I would say, optimal
yeah, but
driving.
By the translation into, at least in the step scenario, if I say I have a larger step, that's, I'm driving my system more, right?
Okay, okay.
So essentially it's like we have an optimal driving.
Yeah, okay. Thank you.
So you will have a tutorial today, or?
They have a question.
Okay, so we'll have a tutorial. Maybe if you have any questions, it can be short also, depending on. Yeah, anyway, you are stuck here till 6:30 for dinner, I guess, right? So, yeah. Okay.